Hello there, and welcome to the Cosmographer. In March of 2015, a team at an Australian radio observatory solved a 17-year-old mystery by microwaving a mug of water and opening the door before the timer finished. That is the shape of this entire list. Every scenario here has been published, with names on it and a date, and almost none of them is the one you have heard before. Number 8 is a paper by the director of a NASA climate laboratory, asking what an industrial civilization on this planet 40 million years ago would have left behind, and finding that the honest answer is a few centimeters of sediment. Number 6 is the standard humanity wrote for itself, permitting less than one chance in 10,000 of delivering a single living microbe to an ocean world, and it is entirely voluntary. Number 4 is an 18-meter rock that has looped around this planet every 45 years for hundreds of thousands of years, and that a spacecraft is holding station beside right now. 10 scenarios, ordered not by how alarming they are, but by how much verified evidence sits behind each one. Get comfortable and settle in. If 3 hours of the universe's open questions is your idea of a good night, a quick like and subscribe genuinely helps this channel reach more curious minds like you. Because by the time we reach number 1, the silence will have stopped being a fact about them. Let's begin at number 10. Number 10, the ones that are sleeping. This list is ordered by evidence. That is the only rule it follows, and it is worth stating clearly before we begin, because it is not the rule most lists of this kind follow. We are going to walk down through 10 scenarios in which we are not alone, or were not alone, or might not be alone in a way we have not thought to check. Each one has been published. Each one has a name attached to it, and a date, and a journal. And they are arranged from the one supported by the least evidence to the one supported by the most. So the scenario we begin with is the one with the most rigorous mathematics and the least observational support of anything on this list. It is a genuine argument made by serious people, and it has a genuine rebuttal from someone whose own work the argument depends on. What it does not have is a single measurement in its favor. That is exactly why it is at number 10, and it is a useful place to start, because it shows what this kind of thinking looks like at its most abstract before we begin the long climb toward the things we have actually measured. The paper is called, and this is its real title, That Is Not Dead Which Can Eternal Lie. The subtitle is The Estivation Hypothesis for Resolving Fermi's Paradox. It was written by Anders Sandberg, Stuart Armstrong and Milan Cherkovich, and published in the Journal of the British Interplanetary Society, Volume 69, pages 406 to 415. It was posted publicly in April of 2017. The title is a line from H. P. Lovecraft. That is not dead which can eternal lie, and with strange eons even death may die. Inside Lovecraft's fiction, the couplet is attributed to a mad Arab named Abdul al-Hazred, and it appears first in a story from 1921 and again in a more famous one from 1928. The authors chose the word estivation rather than hibernation deliberately, and they explain why in a footnote. Hibernation is sleeping through winter. Estivation is the correct word for sleeping through months that are too warm. That distinction is the entire argument in a single word. 2 of the 3 authors were at the Future of Humanity Institute at the University of Oxford. The third holds a joint appointment at the Astronomical Observatory of Belgrade. It is worth noting, gently, that the Oxford Institute that produced this paper was closed in April of 2024, after 19 years. The argument survives. The building it came from does not. Here is what the argument says. Suppose you are a civilization that has already solved the problems civilizations solve. You have spread across a large volume of space. You have gained control of the matter inside it. What do you want to do with the rest of time? The paper's answer is that if what you value is computation, in any form at all, then the rational strategy is to do nothing for a very long time. The physics underneath that claim is a result from 1961. A physicist named Rolf Landauer, working at IBM, showed that erasing one bit of information must dissipate a minimum quantity of energy. The formula is short. It is Boltzmann's constant, multiplied by temperature, multiplied by the natural logarithm of 2. And the important part of that formula is the temperature, because it sits there as a straight multiplier. This is not an engineering limit that better hardware will beat. It is thermodynamics. Put numbers on it, and the shape becomes obvious. At room temperature, 300 Kelvin, erasing one bit costs about 2.87 times 10 to the minus 21 joules. That is a fantastically small number, but it is not zero, and everything scales from it. Now cool the environment to the temperature of the cosmic microwave background, which is 2.725 Kelvin. The same erasure now costs about 2.61 times 10 to the minus 23 joules, roughly 110 times cheaper. Nothing about the computer changed. Only the room did. And the room is still cooling. The measured temperature of the microwave background is 2.72548 Kelvin, plus or minus about half a thousandth, from the FIRAS instrument aboard the COBE satellite, combined with WMAP. That instrument found no departure from a perfect blackbody spectrum anywhere between 70 and 640 gigahertz. It is one of the cleanest measurements in physics. And the number it measures is falling, and under long-term expansion, it falls exponentially rather than gradually. But it does not fall forever. There is a floor set by the horizon of an expanding universe, and the paper puts that floor at about 2.67 times 10 to the minus 30 Kelvin. The background radiation redshifts down to that floor in roughly 1.4 trillion years. Now take the ratio. Today's background temperature, divided by that floor, is almost exactly 10 to the 30th power. That is a 1 followed by 30 zeros. And because the cost of computation scales directly with temperature, that ratio is the multiplier. A civilization that waits gets 30 orders of magnitude more computation out of the same matter than a civilization that spends now. The paper puts the comparison in a form that is easier to hold. The mass energy of Earth alone, 5.9 times 10 to the 24th kilograms, spent in the cold far future, would power more computation than burning the entire present observable universe today. The observable universe weighs about 6 times 10 to the 52nd kilograms. One planet, later, beats everything, now. That is what a factor of 10 to the 30th actually buys. There are further numbers in the paper, and they are worth hearing because they show how carefully the case was built. A supercluster of galaxies with a radius of 50 megaparsecs and a mass of 10 to the 43rd kilograms could be subdivided into around 10 to the 61st bits at the present background temperature. At the far future floor, the theoretical limit rises to 10 to the 75th bits. But bits that small would each have to weigh less than an electron, which is not a thing matter can do, so the realistic ceiling imposed by the chunkiness of atoms is about 10 to the 69th. Even after that correction, the gain is enormous. There is also a point at which the strategy stops improving for a different reason. Below about 10 to the minus 8 Kelvin, error correction stops being limited by heat and starts being limited by quantum tunneling, which does not care how cold the room is. That crossover arrives in roughly 270 billion years. So the practical wait is shorter than the theoretical one, though neither is a number a human mind holds easily. The obvious objection is, why wait at all? If you have trillions of years, why not run some of the computation now and the rest later? The paper answers this directly, and the answer is the reason the strategy is all or nothing. The computational gain grows exponentially with time, which means most of the total value accrues within the final doubling. Spending early does not cost you a little. It costs you almost everything. And because there is a flaw, the strategy avoids what the authors call the paradox of the indefinitely postponed splurge. At some point, the gains stop, and at that point, it becomes rational to actually spend. One worked example gives a sense of the far future scene. A blackbody civilization 50 megaparsecs across, running on 1 single watt of total power, would sit at about 2.8 times 10 to the minus 11 Kelvin and perform 3.8 times 10 to the 33rd irreversible operations per second. 1 watt. That is a dim reading lamp, running an entire supercluster's worth of thought. The paper runs 3 separate versions of what it would mean to burn a supercluster's worth of matter, and the spread between them is the clearest illustration of why patience pays. In the impatient case, you spend everything before protons themselves begin to decay, roughly 10 to the 33rd years from now. That gives you 5.7 times 10 to the 21st watts of continuous output, which is the luminosity of a dim red dwarf star, and it buys you about 10 to the 80th bit erasures. In the maximally patient case, you run at 10 to the minus 75th watts, and you buy 10 to the 115th erasures, which is 35 orders of magnitude more. The catch is the pace. In that version, a single bit erasure takes a pause of about 100 quadrillion years. In the realistic middle case, you run at 10 to the 10th watts, the output of a large terrestrial power plant, for 5.7 times 10 to the 44th years, and you get 10 to the 93rd erasures. The general rule the paper draws from this is that the total number of operations you can afford scales inversely with the 4th root of the power you choose to draw. Slow spending, in other words, produces vastly more total thought if you are willing to be patient about it. The pace is worth sitting with because it is the part that makes the scenario feel genuinely alien. At the floor temperature, the natural clock speed set by quantum mechanics works out to 1 tick every 380 billion years. And a civilization 50 megaparsecs across would need 326 million years just for a signal to cross from one side of itself to the other. That is not a slower version of us. That is something whose single thought takes longer than the interval between mass extinctions on this planet. There is also an intellectual ancestry here that the authors acknowledge openly. Freeman Dyson laid the groundwork in 1979 in the work that founded what is sometimes called physical eschatology, the study of how physics constrains the far future. Dyson proposed hibernation as a way to stretch an energy budget across cosmic time, and 2 other physicists, Lawrence Krauss and Glenn Starkman, published a critique of that approach. So the estivation argument is not a novelty. It is the latest move in a conversation that has been running for nearly 50 years about what the end of the universe permits. One technical caveat belongs here, because the authors raise it themselves and it matters. Reversible computation escapes Landauer's limit entirely, in principle. A logically reversible operation destroys no information and therefore need dissipate nothing, and quantum computation is logically reversible because quantum circuits are unitary. But irreversible steps are unavoidable in 2 places. creating fresh, blank memory costs the full Landauer price for every bit you zero. And actually performing error correction, as opposed to merely computing, costs it too. So the temperature dependence never quite goes away, no matter how clever the architecture. So the estivation hypothesis says the reason we see nothing is that everyone is holding still. Not hiding exactly. Not watching. Simply inactive, on purpose, for economic reasons, waiting for the universe to become a better place to think in. And now the rebuttal, which is where the item earns its place, at number 10, rather than higher. In 2019, 3 researchers published a formal comment in the journal Foundations of Physics. They were Charles Bennett of the IBM Watson Research Center, Robin Hanson of George Mason University, and Jess Riedel of the Perimeter Institute. Hold on to the middle name, because he returns much later in this list, arguing something almost opposite. But it is the first name that matters here. Charles Bennett is the co-originator of reversible computing. He is one of the people who worked out how information and thermodynamics fit together in the first place. The rebuttal comes from the person whose own theorem the estivation argument leans on. Their objection is not about the arithmetic. The arithmetic is fine. Their objection is that the argument quietly assumed something untrue about where entropy goes. Sandberg and his colleagues treated the cosmological background as the only place a computer can dump the disorder it produces. And Bennett's group pointed out that it is not. The universe today is full of reservoirs sitting in non-maximal entropy states. Stars, gas clouds, temperature differences of every kind. Entropy can be transferred into those, at a rate of 1 bit of order, spent per bit of error erased, and it can be done now, at any time, with no reference to the background temperature at all. They named the specific error, and it is a precise one. The original argument treated a reservoir's total internal energy as though all of it were free energy, available to do useful work. That is a conflation of energy with free energy, and it produces a reservoir that can do enormous work while accepting no disorder in return, which is not a thing that exists. Their constructive version is simple enough to picture. Take any 2 systems at different temperatures. Run a heat engine between them. The work that engine produces powers a device that erases bits, pumping the disorder into the colder side. The total number of erasures you get equals the order the reservoir started with, measured in bits. No waiting required. Their conclusion is worth quoting almost exactly because it inverts the original entirely. A civilization capable of reversible computing, they wrote, has no incentive to estivate until after it has taken control of and fully exploited all accessible matter in the universe. Which means the falling background temperature is not an argument for sleeping. It is an argument for grabbing as much of the universe as possible, including the parts that are already thermalized and inert, because those parts are storage. They closed with a speculation they clearly enjoyed, and it is too good to leave out. It has not escaped our notice, they wrote, that dark matter may have a purpose for a powerful civilization able to produce it. A way to temporarily sequester most of the mass of the universe in a form whose dynamics conserves energy, angular momentum, and, to a good approximation, entropy. A savings account made of something that does not interact. They also generalized the objection beyond computing, which strengthens it considerably. The same logic applies to any goal whose limiting cost is residual friction of some kind. Their own example, and they seem to have chosen it for pleasure, was galactic-scale art projects. If waiting does not help you compute, it does not help you build either. Both Riedel and Hanson wrote public explanations of the argument in the months afterward, Riedel in August of 2019, and Hansen under a title that summarizes the whole position in 5 words. Aliens need not wait to be active. They were also honest about what they had not addressed. They did not treat the slowing of thermalization as photon density drops, or the ultimate limits of insulation, or the finite size of atoms. And no published counter-rebuttal from the original 3 authors has appeared. So the exchange stands as it is. One argument, one serious objection to it, and silence since. Nobody has conceded anything. Which leaves this scenario exactly where a scenario belongs at number 10. It is elegant, it is internally consistent, it makes a testable claim about what we should see, and the thing it predicts we should see is nothing at all. That is the weakest possible position for an idea to occupy, and the authors would not disagree. Their own list of assumptions runs to 6 items, and the last one is the one that matters most for our purposes. Estivation, they wrote, must be largely invisible. If they are right, then every telescope hour humanity has ever spent looking for activity was looking for the wrong thing. The correct search would be for absence, held very carefully in place, across a volume of sky, for longer than our species has existed. We do not have an instrument for that, and it is not clear what one would look like. But the next scenario on this list requires no civilization to make any choice at all. It does not need patience, or coordination, or a strategy. It only needs a planet to be slightly larger than the one we are standing on. Number 9. The worlds that cannot leave. Every scenario about other civilizations has a hidden assumption buried in it, and the assumption is almost never examined. The assumption is that if someone out there wanted to leave their planet, they could. We assume it because we did it. We assume it because the first step off a planetary surface feels like a matter of will and engineering, and both of those feel like things a determined species eventually gets around to. The scenario at number 9 says that assumption is a coincidence of where we happen to live. And unlike the previous entry, it does not require anyone to make a choice. It does not require patience or coordination or strategy. It requires only that a planet be somewhat larger than this one, and it is enforced by an equation published in 1903. The paper is called Spaceflight from Super-Earths is Difficult. It was written by Michael Hipke of the Sonneberg Observatory in Germany, posted in April of 2018, and published in the International Journal of Astrobiology the following year. An earlier version of the preprint carried a title with a typo in it, which is a small human detail worth keeping, because the argument itself is anything but sloppy. The equation underneath it belongs to Konstantin Tsiolkovsky, the Russian schoolteacher who worked out the mathematics of rocket flight decades before anyone flew one. His result is short. The change in velocity a rocket can achieve equals its exhaust velocity multiplied by the natural logarithm of the ratio between its fueled mass and its empty mass. That is the whole of it. Now invert it, because that is the form that matters here. If you know the velocity you need, the mass ratio you require is an exponential function of that velocity. Not a proportional one. Exponential. Every extra kilometer per second you need does not add to the fuel bill. It multiplies it. And escape velocity rises with planetary mass. So the fuel required per unit of payload scales in Hipke's own formulation as roughly 3.3 times e to the power of surface gravity measured in Earth gravities. That exponent is where the entire scenario lives. Start with the number we know. Earth's escape velocity is 11.186 kilometers per second. That is the speed at which an object, given no further push, coasts away from this planet forever. Everything humanity has ever sent to another world had to reach it. Now take a world 10 times the mass of Earth, with a radius 1.7 times ours. That is roughly the densest plausible super-Earth, and Hipke uses a real planet as his anchor, a world called Kepler 20b, in a system 922 light-years away, announced along with 4 siblings in December of 2011. Its measured figures are about 1.87 Earth radii and 9.7 Earth masses. At that radius, it would normally be filed as a small gas planet. Its mass forces an iron-rich rocky interpretation instead. Escape velocity from that world is 27.1 kilometers per second, 2 and a bit times Earth's. Surface gravity is 3.46 times ours, which is heavy but not crushing. A person could stand there. A person could walk slowly and build things. But now run the exponential. An idealized single-stage rocket on Earth, with a specific impulse of 350 seconds, and ignoring the weight of the rocket's own structure, needs a mass ratio of about 26. The same idealized rocket on that super-Earth needs a mass ratio of about 2,700. Hipke's own summary sentence is that such a rocket must burn 104 times as much fuel for the same payload. 2,700 tons of fuel for every ton of cargo. And he is careful to say, immediately, that this is a lower limit that can never actually be achieved because it ignores the mass of the rocket itself. Real multi-stage rockets that reach Earth escape run mass ratios between 50 and 150. So use a realistic figure of 83, and the numbers move from difficult to something else. 1 ton of payload requires about 9,000 tons of fuel. 6.2 tons, which is the mass of the James Webb Space Telescope, requires about 55,000 tons, which Hipke compares to the largest ocean battleships ever built. And 45 tons, which is the mass of a classical Apollo mission to the Moon, requires about 400,000 tons. His comparison for that one is the Pyramid of Cheops. That last figure has become the famous number from this paper, and it is almost universally misquoted, so it is worth getting right. 400,000 is a mass in tons of rocket. It is not a propellant to payload ratio. The implied ratio is closer to 8,900 to 1. Popular retellings that describe a 400,000 to 1 fuel requirement have simply misread the paper. The real ratios in Hipke's own text are around 2,700 to 1 in the impossible ideal case, and around 9,000 to 1 in the realistic one. Those are quite bad enough. For comparison, the vehicles we actually built sit at the easy end of that range. The Saturn V weighed 3,050 tons and put 45 tons on a lunar trajectory, a mass ratio of 68. The Falcon Heavy weighs 1,400 tons and lifts 16.8, a mass ratio of 83, which means the payload is about 1% of what leaves the pad. That is what an easy planet looks like. 1%. The follow-up work is where the picture gets more interesting, rather than simply worse. In May of 2018, Alex Howe at the University of Michigan recomputed the whole thing with better assumptions. At a specific impulse of 400 seconds, the required mass ratio for 27.1 kilometers per second is 1,006. At 350 seconds, he reproduces Hipke's 2,700 exactly. At 450 seconds, it falls to 466. And then he goes further and tries the best chemistry that has ever been fired. There is a tripropellant of lithium, fluorine, and hydrogen, test-fired in 1968, which holds the record for chemical-specific impulse at 542 seconds. It is monstrously toxic and was never flown. With that propellant, the required mass ratio falls to 164. Howe's verdict on that number is that it remains economically hopeless. His most vivid consequence is this. Even a Saturn V, if it could somehow be built and flown from a large super-Earth, could place less than 3 tons on an escape trajectory. The same vehicle that carried 3 people and a lunar module to another world would, on a heavier planet, struggle to lift a car. But Howe also supplies the qualifier that almost every popular account of this work dropped, and it changes the meaning of the whole scenario. Escape velocity and orbital velocity are not the same problem. Orbital velocity is escape velocity divided by the square root of 2, which on that world is 19.2 kilometers per second. At a specific impulse of 400 seconds, reaching orbit needs a mass ratio of 134. Howe's own assessment of that figure is that it is still more difficult than launching from Earth, but readily achievable with current technology. So a civilization on a large super-Earth is not trapped on the ground. That is the version that circulated in the press, and it is wrong. They can reach orbit. They can build stations and satellites and telescopes and everything that follows from being in space around your own world. What they cannot easily do is leave. They are not imprisoned. They are priced out of the last step. That is a sharper claim, and a stranger one, because it describes a civilization that can see everything and reach nothing. There are secondary arguments in the paper, and several of them are quietly excellent. Launching from mountains, for instance, barely helps. Rocket thrust does improve in vacuum, but for the space shuttle's main engine, the difference between sea level and vacuum is only about 25%. Worse, atmospheric pressure below about 0.4 bar is not survivable long-term, and higher gravity compresses an atmosphere, so those low pressures occur at lower altitudes on a heavier world, not higher ones. The mountain does not get you as far up as you think. Hipke's suggested workaround is artificial mountains, built as launch platforms. He also notes that more massive planets should have shorter mountains, since rock can only hold itself up against so much weight, and he points out that this should eventually be measurable in transit observations by future telescopes. Our own system supports the pattern neatly. The tallest features anywhere near us sit on low-gravity bodies. The central peak of Rhea Silvia on the asteroid Vesta reaches 22 kilometers. Olympus Mons on Mars reaches 21.9. Neither could exist on a world like the one in this scenario. Space elevators, which are the obvious thought when someone says the rocket equation is the problem, are ruled out. Carbon nanotubes are the strongest material we know of, and they are, in Hipke's phrase, just barely sufficient for Earth's gravity. If nothing stronger is physically possible, then on a super-Earth, the only remaining option is nuclear propulsion, and he names the American nuclear thermal rocket program that was developed and then abandoned in the early 1970s. Ocean worlds get their own treatment, and it is the most enjoyable passage in the paper. If your planet has no dry land, you launch from floating platforms, or you launch from underwater, using explosives to flash vaporize water into steam, which is roughly how submarine-launched missiles already work. Hipke then delivers the line that gives the whole paper its charm. These aquatic complications, he writes, make the theory of oceanic rocket launches appear at first quite alien. Presumably, land-based launches seem equally human to alien rocket scientists. And there is a rescue, which is why this scenario sits at number 9 rather than higher. Howe's counter-proposal is a momentum exchange tether, an idea that goes back to Hans Moravec in 1977. You put a long rotating cable in low orbit. A suborbital rocket flies up, docks with the lower end, is swung around, and is released at much higher speed. The cable loses a little orbital energy each time and can be topped up electrically. The numbers are surprisingly forgiving. Such a tether would cut the velocity a chemical rocket must supply for escape by 40%, from 27.1 down to 16.3 kilometers per second. The mass ratio for that is 64, which is essentially the Saturn V's 68. The tether needs to be a few hundred kilometers long, against roughly 100,000 kilometers for a true space elevator. And the bootstrapping requires exactly one conventional launch. A seed tether goes up on a rocket that can reach low orbit unassisted, and robotic climbers arriving on cheap suborbital rockets thicken it from there. Applied to Earth, the same idea is almost embarrassing. Kevlar-class fibers, which already exist and are already manufactured in quantity, would cut the velocity needed to reach orbit from 7.8 to 4.8 kilometers per second, and the velocity needed to escape from 11.2 to 5.2. That is a mass ratio as low as 3.25. Howe's line is that even a suborbital rocket could then reach interplanetary space. There is one demanding detail in the tether scheme, and it is the kind of detail that separates a concept from a plan. The rocket has to reach the descending end of the cable and lock on within a window of a few seconds. Miss it, and you have a suborbital vehicle with nowhere to go. But once the docking is achieved, the arithmetic afterward is remarkable. Reaching the tether from that world costs 13.8 kilometers per second, and escaping from the tether costs only a further 2.5, which is less than the 3.4 kilometers per second it takes to escape from low orbit here at Earth. There is also a limit at the small end of this whole discussion, and it is worth naming because it bookends the argument nicely. There is a size, sometimes called the potato radius, at about 238 kilometers, above which a body's own gravity pulls it into a sphere and tall mountains begin to crush themselves under their own weight. Below that size, worlds can be any shape they like, and launching from them is trivial. Above it, geometry starts charging rent, and it charges more the larger you get. It is worth saying plainly that the press coverage in April of 2018 got this almost uniformly wrong. The headlines announced that aliens on super-Earths are trapped by gravity, which the paper does not say and how explicitly disputes. What the work actually establishes is narrower and more durable. The cost of the last step is exponential in surface gravity, and most rocky worlds have more surface gravity than ours. So the honest verdict on this scenario is a partial one, and Howe states it himself. For the largest super-Earths, most proposed launch systems short of nuclear propulsion would range from infeasible to impossible for reaching escape velocity. Although reaching low orbit would be possible, why does any of this matter for a list about who else is out there? Because of what the planet census now looks like. The most common known class of planet in the galaxy is not a world like Earth. It is a world between Earth and Neptune in size, and hundreds were found by the Kepler mission alone. That population splits cleanly in two, at a feature discovered in 2017 and known as the Radius Valley, or sometimes the Fulton Gap. It is a measured scarcity of planets between about 1.5 and 2 Earth radii. Below the gap sit rocky super-Earths. Above it sit small worlds with thick gas envelopes. The usual explanation is that radiation from the star stripped the envelopes off the lower group. The transition between rocky and gaseous sits at about 2 Earth radii, plus or minus 0.6. Which means the rocky worlds most likely to exist, in the largest numbers, across the galaxy, are worlds heavier than this one. Not dramatically heavier. just enough for the exponent to bite. There is a philosophical question at the bottom of Hipke's paper, and he asks it directly, borrowing a phrase from Leibniz. Do we inhabit the best of all possible worlds? His own answer is that Earth might well turn out to be one that is only marginally habitable. He cites the idea of superhabitable worlds, planets with flatter topography, shallower oceans, and thicker atmospheres that shield better against cosmic rays. Better places to live, harder places to leave. That is the shape of this scenario, and it is why it is genuinely uncomfortable rather than merely interesting. It does not require a filter that kills anyone. It does not require a war, or a collapse, or a decision. It requires only that the first step off a planet costs what chemistry says it costs, and that most planets charge more for it than ours does. Earth's escape velocity is a number nobody chose and nobody earned. It sits just barely on the affordable side of a line, and the line was drawn by the strength of chemical bonds and the shape of an exponential curve. That scenario at least assumes there is someone out there to be stuck on a surface. The next entry asks a much closer question. It asks whether there was ever someone here. Number 8. The civilization that left no fossils. At number 8, the list changes character, and it is worth flagging the change as it happens, because the remaining 8 entries all share a property the first 2 did not. From here on, every scenario is about detection. Not about whether someone is out there, but about whether we would know. And this entry makes that turn by asking the question in the closest possible place. Not another star. Not another planet. Here. The paper is titled The Silurian Hypothesis, and its subtitle is The Actual Question. Would it be possible to detect an industrial civilization in the geological record? It was written by Gavin Schmidt and Adam Frank, posted in April of 2018, and published in the International Journal of Astrobiology. The authors matter here more than usual. Adam Frank is an astrophysicist at the University of Rochester, and he will return much later on this list, arguing something quite different. Gavin Schmidt is the director of the Goddard Institute for Space Studies, the climate modeling laboratory in New York, a post he took over from James Hansen. He is a climate modeler by training, not an astrobiologist. That is not incidental. It is the reason the paper works. This is a detectability argument about the sedimentary record, written by someone who reads the sedimentary record for a living, wearing a science fiction costume. The acknowledgements section is 1 line long, and it reads, "In full, no funding has been provided nor sought for this study." 2 established scientists did this in their own time because the question would not leave them alone. The name comes from a 1970 episode of the British television series Doctor Who, in which a buried race of intelligent reptiles is woken by an experimental nuclear reactor. The authors add a footnote, clarifying that they are not suggesting intelligent reptiles actually existed in the Silurian age, nor that experimental nuclear physics is liable to wake them from hibernation. The fictional creatures were not even Silurian. It is a bad name, and they kept it anyway. Here is the question, stated as they state it. If an industrial civilization had existed on Earth many millions of years prior to our own era, what traces would it have left, and would they be detectable today? They define an industrial civilization precisely, so the question can be answered rather than merely discussed. It is the ability to harness external energy sources at global scales. That is it. Not cities, not language, not technology of any particular kind. Energy at planetary scale. Their window runs from the emergence of complex life on land in the Devonian about 400 million years ago to the Middle Pliocene about 4 million years ago. Purely oceanic societies are out of scope, and so are non-industrial ones. And they establish the baseline that makes the whole exercise vertigo-inducing. Our industrial civilization has lasted, so far, roughly 300 years. Against 400 million years of complex life on land, 300 years is less than 1 part in a million. Whatever we are a very short event. Now the central number, and it is the one to hold on to, because it will come back at the end of this list in a different form. Effective sedimentation rates in ocean cores that contain sediment millions of years old are, at best, a few centimeters per 1,000 years. Which means that the entire industrial era, read by a geologist 100 million years from now, will appear as a section a few centimeters thick, arriving almost instantaneously. Everything we have built, every city, every road, every mine, every launch, every war, every argument about any of it. A few centimeters. You could cover the whole of it with 2 fingers. The second number is about how little of this planet's surface is even old enough to check. The oldest extant large-scale land surface on Earth is in the Negev Desert, and it is approximately 1.8 million years old. Everything older has been buried, uplifted, eroded, subducted, or ground away. In the oceans, because the crust is continuously recycled, sediment evidence only exists for periods after the Jurassic, about 170 million years ago. Anything older than that is simply gone, along with the seafloor it sat on. And the fraction we have actually examined is smaller still. The current area of urbanization on this planet is less than 1% of its surface. Exposed sections and drilling sites for surfaces older than the last few million years are, in the author's phrase, orders of magnitude less as fractions of the original surface. Their conclusion follows directly. For potential civilizations older than about 4 million years, the chances of finding direct evidence of their existence through objects or fossilized examples of their population is small. The fossil arithmetic makes that concrete in a way that stops you. For all the dinosaurs that ever lived, they write, there are only a few thousand near-complete specimens. Equivalently, a handful of individual animals across thousands of species per 100,000 years. And then the line that lands hardest. Species as short-lived as Homo sapiens, so far, might not be represented in the existing fossil record at all. We might not fossilize. Not as a species. Not once. Their analogy for artifacts is the Antikythera mechanism, the geared bronze astronomical calculator recovered from a shipwreck, built around 205 BCE. It is a unique object until the Renaissance. One surviving example of an entire technology, and if the sponge divers had gone somewhere else in 1900, we would have no reason to think that technology had ever existed. To be fair, the recent record is much better. Surfaces from the last 2.5 million years do preserve widespread evidence. Soil horizons, climate records, the archaeology of Neanderthals and Denisovans, and bipedal hominid footprints at Laetoli, pressed into volcanic ash and dating back to at least 3.7 million years. If someone had walked here 4 million years ago, we would probably know. 40 million is a different question entirely. So they do the sensible thing. They go and look at what a global carbon release actually leaves behind, using the closest natural analog in the record. The Paleocene-Eocene thermal maximum happened about 56 million years ago. It is one of the best studied intervals in the history of this planet, and the shape of it is unnervingly familiar. The carbon went in fast. Perhaps less than 5,000 years for the injection. Temperatures rose by 5 to 7 degrees Celsius, and by some multi-proxy reconstructions as much as 8. The whole sequence of events lasted between 100,000 and 200,000 years. There is a negative spike in carbon isotopes of more than 3 parts per thousand, recorded at more than 130 separate localities around the world, across every kind of depositional environment. Carbonate preservation in the upper ocean decreased. Kaolinite clay increased in many sediments, which is a signature of erosion, though whether the increase was truly global remains argued over. Life responded. Between 30 and 50% of bottom-dwelling foraminiferal species went extinct. That is the only major deep-sea benthic extinction in the entire Cenozoic era, the whole 66 million years since the dinosaurs. Diversity in the Pacific dropped by about 30% at onset. And at the same time, on land, mammals and lizards expanded dramatically across North America. Something died in the dark, and something else inherited the daylight. The attributed cause is the intrusion of a large igneous province into organic sediments, essentially a continent-scale volcanic event cooking buried carbon. Estimates of how much carbon went in range from about 2,000 to 7,000 gigatons, and the volcanic version of the story implies more than 10,000. And here is the sentence in the paper that does the real work. Compared to the hypothesized Anthropocene signature, almost all changes found so far for the PETM are of the same sign and comparable magnitude. The same sign and comparable magnitude. There is one discriminator, and it is rate. The carbon injection at that event probably ran somewhere between 0.3 and 1.7 petagrams of carbon per year. The current human rate exceeds 10 gigatons per year, roughly an order of magnitude faster than the fastest natural warming event of the last 66 million years. We are doing it faster, considerably faster, but rate is precisely the thing that smears out. In a few centimeters of sediment, worked over by burrowing animals for 100,000 years, the difference between 5,000 years and 300 years is not a difference you can read. Both are instantaneous. Both are a line. Let us stand in it for a moment, because the numbers are easier to feel from inside them. It is 56 million years ago. The sea here is shallow and very warm, warmer than any tropical water on the modern Earth, and it has been getting warmer for centuries, in a way nothing living here has any way to notice. The air is thick. There is no ice at either pole. On the seabed, in the dark, the small-shelled organisms that have carpeted the ocean floor for tens of millions of years are failing, species by species, as the water acidifies around them and the oxygen thins. There is no violence in it. There is no event to point at. There is only chemistry, arriving slowly enough that nothing on this seabed could be said to be dying quickly, and fast enough that a third of everything here will not exist in 100,000 years. Above the water, along a coastline that has no name and will leave no map, the land is doing well. Forests are expanding. Mammals are spreading north into terrain that was closed to them for millions of years. Whatever this is, it looks, from the surface, like a good century to be alive. And now pull back and up and forward, 56 million years, into a room with fluorescent lights and a laboratory bench, where a core of ocean sediment lies split along its length. Somewhere in that core, the entire sequence, the carbon, the warming, the acidification, the extinction, the recovery, occupies a band about 2 centimeters wide. A technician could put a thumb over it. That is what a planetary-scale carbon release looks like when you read it afterward. It looks like a line. And that event is not alone. The authors work through a whole catalogue of comparable intervals, because the point is that the record is full of these. In the 6 million years after the warming event, there were at least 4 or 5 more peaks, each with its own negative carbon spike, its own warming, its own increased sediment delivery from the land. They are known collectively, and the acronym is a small joke, as the Eocene layers of mysterious origin. The authors add a footnote conceding that most things that happened 50 million years ago will forever remain somewhat mysterious. There is another warming around 40 million years ago. And they add one more observation that ought to be quoted more often than it is. At least since the Carboniferous, 300 to 350 million years ago, there has been sufficient fossil carbon on this planet to fuel an industrial civilization comparable to our own. The fuel has been in the ground, available, for 300 million years. We are simply the first ones we know of to have dug it up. There is a formal reason they framed the paper this way, and it connects to the equation that has organized this entire field since 1961. In the Drake equation, the fraction of life-bearing worlds that produce a civilization has always been treated as having a value on Earth of exactly 1. If more than one industrial civilization can arise on a single planet across its lifetime, that term can exceed 1. It is the only term in the whole equation for which we have ever had a confirmed measurement, and the paper's real provocation is that we might not even have that. So what would we leave that the PETM did not? The authors go through it carefully, and the honest answer is, not much, but not nothing. Most of our markers are indistinguishable from natural events. The carbon isotope shift, the warming, the nitrogen cycle disruption, the changes in sedimentation and mineralogy, the faunal turnover. All of it happens naturally. Some of our markers are too short-lived to matter at all. Gas concentrations in ice cores do not survive multi-million-year timescales because the ice does not. But their summary verdict is the interesting one. Most of the individual markers will not be unique in the context of Earth history, but the combination of traces may be. 2 categories stand out. The first is plastics. Since 1950, there has been a very large increase in plastics entering the ocean. The buoyant common polymers, polyethylene and polypropylene, are mechanically eroded into micro and nanoparticles rather than chemically destroyed. Plastic litter has now been surveyed on the seafloor from coastal shelves to deep basins to the Arctic. On beaches, a genuinely new kind of rock has been found and named, called plastiglomerate, formed where plastic-containing debris meets high temperatures and fuses with sediment and organic debris. Degradation is mostly by solar ultraviolet in the sunlit layer, and it slows drastically once particles are weighed down by fouling organisms and sink. The author's verdict is that the potential for very long-term persistence and detectability is high. The second is radioactivity, and it is the sharpest single marker on the list. Most of what a nuclear age produces decays away in human timescales. But 2 isotopes are long-lived enough to be read across geological time. Plutonium-244 has a half-life of 80.8 million years. Curium-247 has a half-life of 15 million years. Either would be detectable across a large fraction of the relevant window if deposited in sufficient quantity, which the authors note would follow from a nuclear weapon exchange. And plutonium-244 has one property that makes it close to a fingerprint. There are no known natural sources of it outside of supernovae. The proof that this kind of reading works already exists, and it is 2 billion years old. In the Franceville Basin at Oklo, in Gabon, uranium ore lay in rock that was oxygenated and full of groundwater, and around 2 billion years ago, natural nuclear fission began and ran, on and off, for a very long time. Nothing at Oklo is left of the transuranic elements. They decayed away hundreds of millions of years ago. But the uranium there is measurably depleted in its fissionable isotope, and the ratios of the fission products are still readable in the rock. We know fission happened there, unambiguously, from a 2 billion year distance, with no equipment left behind and no isotopes surviving. That is the paper's proof of concept, and it is a good one. A nuclear event, 2 billion years old, still legible. There is one more marker, and it links this entry directly forward to the next one on this list. Most total synthesis pathways in chemistry do not discriminate between left-handed and right-handed versions of a molecule. They produce both in equal measure. Biology does not work that way. Naturally occurring amino acids are all left-handed, and almost all sugars are right-handed. So a mixture with equal amounts of both hands, found in a place where biology would only ever have made one, is a fingerprint of industrial synthesis. Handedness is a signature. Two other findings deserve to be heard, because they are the passages people remember. The first is what might be called the self-limitation paradox, and the logic of it is a closed loop. The longer a civilization lasts, the larger the signal you would expect in the record. But the longer a civilization lasts, the more sustainable its practices must have become in order to survive that long. And the more sustainable a society is, the smaller its footprint on the rest of the planet. And the smaller the footprint, the less signal ends up in the rock. Their conclusion is that the footprint of civilization might be self-limiting on a relatively short timescale. Success erases you. The second is stranger, and the authors offer it as speculation. Large carbon releases often trigger ocean anoxia through increased nutrient supply, which causes massive burial of organic matter, which eventually becomes source rock for fossil fuels. Which means, they write, that prior industrial activity would have actually given rise to the potential for future industry via their own demise. Each civilization, in ending, buries the fuel for the next one. And then they do the thing that makes this a real paper rather than a provocation. They tell you not to believe it. One would be able to fit any observations to an imagined civilization in ways that would be basically unfalsifiable, they write. Care must be taken not to postulate such a cause until actually positive evidence is available. The Silurian hypothesis cannot be regarded as likely merely because no other valid idea presents itself. And more plainly still, perhaps unusually, the authors of this paper are not convinced of the correctness of their proposed hypothesis. What they actually did was propose 3 tests, and all 3 are ordinary science. Study how long uniquely industrial byproducts persist in ocean sediment. Re-examine existing sediment sections from past events, specifically looking for elemental anomalies normalized against weathering fluxes so that artificial enhancement of metal production would stand out. And only if unexplained anomalies turn up, ask whether there are candidate species in the fossil record and what became of them. That is the same procedure that found the iridium layer at the end Cretaceous boundary and confirmed the asteroid. It worked there. It has been tried at the warming events and has found nothing. What they said about other planets is usually misreported too, so it is worth quoting. They note that abundant evidence exists of surface water in ancient Martian climates, and that early Venus may have been habitable between about 2 billion and 700 million years ago, when the sun was dimmer. And they suggest that deep drilling operations could conceivably be carried out on either planet in future to assess their geological history. Drilling. Not artifact hunting. The moon is not discussed in the paper at all. So this scenario sits at number 8 because the evidence for it is exactly 0, and the argument about detectability is exactly sound. Nobody has found a 200-million-year-old anomaly. Nobody has looked very hard, because until this paper, nobody had written down what to look for. And the question underneath it turns out not to be about reptiles at all. It is about whether anything we have done will still be legible when the layer we are currently making has finished being made. And if a whole civilization could vanish from the record of this planet, it is worth asking what else on this planet we have never actually looked for. Number 7. The life we are not equipped to see. The previous entry established that a civilization could disappear from this planet's record. This one goes further and asks a question that is in some ways more unsettling, because it does not require anything to have disappeared at all. It asks whether a completely separate origin of life could be alive on Earth right now, in ordinary places, in quantity, and be invisible to us for a reason that has nothing to do with where it is hiding. The idea has a name. It is called a shadow biosphere, and it means a microbial biosphere on this planet running on radically different biochemistry from everything we know. Not a strange branch of the tree of life. A second tree with no common ancestor, sharing the same rocks and the same water and the same 4 billion years. It emerged in 2 papers, both published in 2005. One by Carol Cleland and Shelley Copley, titled The Possibility of Alternative Microbial Life on Earth. The other by Paul Davies and Charles Lineweaver, titled Finding a Second Sample of Life on Earth. Cleland is a philosopher of science at the University of Colorado, and it is not an accident that a philosopher is at the center of this. The argument is about the structure of evidence. 4 years later, the group consolidated it into a paper called Signatures of a Shadow Biosphere, with 6 authors: Davies, Cleland, Lineweaver, the chemist Stephen Benner, the planetary scientist Chris McKay, and a young researcher named Felisa Wolf-Simon. Remember that last name. Here is the argument, and it is far stronger than it initially sounds. We have 2 ways of finding out what lives in a sample of soil or water. The first is to grow it. You take the sample, you plate it on a medium, and you count the colonies. The second is to sequence it. You take the sample, you amplify a particular gene that all known life shares, and you read what comes back. The first method has a known and enormous failure rate. It is called the Great Plate Count Anomaly, and it has been recognized since the 1980s. Count the cells in an environmental sample directly, under a microscope, and then count the colonies that grow from the same sample. The 2 numbers do not agree. They do not even come close. The accepted gross estimate is that as little as 1% of microbial species in a given ecological niche are culturable. 1%. 99 out of 100 organisms in a given place simply do not grow on anything we have tried to grow them on. That uncultured majority has a name of its own. It is called microbial dark matter, and it is ubiquitous and abundant across every ecosystem anyone has examined. It is genuinely enormous, and it is not controversial. It is simply the state of the field. Now, that failure is exactly what the second method was invented to fix. If you cannot grow them, sequence them where they lie. The standard workhorse is amplification of the 16S ribosomal RNA gene using what are called universal primers, short pieces of DNA that latch onto a conserved region and let the machinery copy what follows. And here is where the argument closes. Those primers were designed against the sequences of organisms we already knew about. They are universal in the sense that everything we have found so far matches them, which means an organism whose ribosomal sequence has diverged far enough would not be amplified. It would not appear, it would return nothing, and nothing looks the same as absence. And it is worse than that. Benner and his colleagues made the point sharply in 2004. If organisms from an RNA world ever existed, they might still be alive and unnoticed, because they would contain no ribosomes at all. And ribosomal markers are precisely what our detection relies on. So put the two together, and you get the claim that this entry rests on. We have never run an unbiased census of life on Earth. Both of our survey instruments, the Petri dish and the ribosomal primer, assume in advance the biochemistry they are meant to detect. The instrument decides the answer before the question is asked. What might a shadow organism differ in? The literature catalogues the options. A different set of amino acids, different bases or sugars in the genetic polymer, a different genetic code, a polymer that is neither DNA nor RNA, arsenic in place of phosphorus, or the simplest and strangest option of all, the same chemistry but built the other way round, in mirror image. Where would you look? Benner proposed 3 kinds of place. Environments low in sulfur, spatially constrained environments, meaning minerals with pores smaller than a micrometer, and environments that cycle between extreme heat and extreme cold. Others have proposed the deep subsurface and hypersaline brines. And Cleland has a specific candidate she keeps returning to, which is desert varnish. Desert varnish is the dark coating that forms on rock surfaces in arid regions. It is thin, it is glossy, it takes thousands of years to form, and its status as biological or non-biological has been argued over since Darwin's time. It is not exotic. It is on rocks in the Mojave and in the Sinai, and probably somewhere within driving distance of most people listening to this. And nobody knows for certain what makes it. It is worth noting that the uncultured majority has already paid out at least once. A new class of antibiotic, Teixobactin, was discovered from an organism nobody had ever managed to grow. The 99% is not a theoretical reservoir. It is a place where things are found. Now the test. There is a bacterium called GFAJ1, a rod-shaped salt-loving organism isolated from sediment at the bottom of Mono Lake in eastern California. Mono Lake is an extraordinary place chemically. It is hypersaline at about 90 grams of salt per liter. It is highly alkaline at a pH of 9.8. And it carries one of the highest natural arsenic concentrations of any body of water in the world, at 200 micromolar. The strain designation stands for Give Felisa a Job. The name is attributed to Paul Davies, and it was a joke about a young researcher's employment prospects. Felisa Wolf-Simon isolated and cultured it from 2009, while a NASA astrobiology fellow in residence at the United States Geological Survey in Menlo Park, California. She was working directly from the Shadow Biosphere program. The year before GFAJ1, she had co-authored a theoretical paper asking whether nature might also have chosen arsenic. She made a prediction and then went to the one place on Earth where you would test it. On the 29th of November, 2010, NASA issued a media advisory announcing a news conference that would, in its own words, impact the search for evidence of extraterrestrial life. The conference was held on the 2nd of December. The release that day was headlined, NASA Funded Research Discovers Life Built with Toxic Chemical. The claim was that when starved of phosphorus, this organism substitutes arsenic for a small percentage of it, incorporating arsenic into its metabolites and its large molecules, and continuing to grow. If true, it would have been the first organism found to break a rule everyone had assumed was universal. Phosphorus is in the backbone of DNA. It is in the energy currency of every cell. Substituting arsenic for it is not a variation. It is a different chemistry of life. The objections began within days, and they came from three directions at once. The first was the data in the paper itself. The phosphorus-free growth medium was not phosphorus-free. It contained about 3.1 micromolar residual phosphate from reagent impurities. The arsenic-fed cells carried phosphorus at 0.019% of dry weight, which is 1/30th of normally fed cells, but is not zero. And an ion probe measurement in the same study implied a roughly 75-fold excess of phosphorus over arsenic, even in the arsenate-grown cells. Growth in arsenate ran at 60% of the normal rate. There was no isotope-labeled phosphate control. And there was no direct evidence of arsenic inside any biological molecule. The second was chemistry, and it was decisive, and it predated the paper by decades. There is a landmark article from 1987 titled "Why Nature Chose Phosphates," and its answer is stability. Arsenate esters fall apart in water orders of magnitude faster than phosphate esters do. The arsenic version of one of DNA's building blocks has a half-life of 40 minutes in water at neutral pH. And a kinetics paper published in 2011 estimated the half-life of an arsenic-linked bond in the DNA backbone at as short as 0.06 of a second, against 30 million years for the phosphorus version. 0.06 of a second, against 30 million years. Alex Bradley at Harvard put the consequence plainly. Arsenic-containing DNA would be so unstable in water that it could not have survived the paper's own extraction procedure, which involved 5 aqueous steps and an ethanol precipitation. The molecule could not have made it to the instrument. The third came from a blog. Rosemary Redfield, a microbiologist at the University of British Columbia, posted a detailed technical takedown 2 days after the press conference. She wrote that the paper did not present convincing evidence that arsenic had been incorporated into DNA or any other biological molecule, and that the experiments lacked necessary washing steps and controls. It is a landmark case of post-publication peer review conducted in public, in real time, by someone with no institutional stake. And then she did the part that mattered. She obtained the strain and worked through the methods herself. She found the organism grew better on solid agar than in liquid, and traced that to low potassium in the medium rather than anything to do with arsenic. She corrected the ionic strength, corrected the pH, and switched from plastic tubes to glass. With those fixed, arsenate only marginally stimulated growth and did not affect final culture densities. And in January of 2012, her mass spectrometry of the organism's DNA detected no arsenic at all. On the 8th of July 2012, 2 formal refutations appeared back-to-back in the same issue of the same journal that had published the original. One from Redfield's group. One from a Swiss team whose title stated the conclusion without ornament. GFAJ1 is an arsenate-resistant, phosphate-dependent organism. A month later, the mechanism was published. Arsenate induces massive breakdown of the cell's own ribosomes. The organism was almost certainly recycling phosphate from its own dismantled machinery, which is why it could grow in a medium that appeared to have none. It was not eating arsenic. It was eating itself. 8 technical comments ran in the journal in mid-2011, accompanied by an editor's note conceding that some issues remained and that their resolution was likely to be a long process. That process ended on the 24th of July, 2025. The paper was retracted almost 15 years after publication. The retraction found no evidence of misconduct by the researchers. The stated basis was that the conclusions were not supported by the data. And 10 of the original authors, including Paul Davies, published a response alongside it, arguing that the journal had gone beyond the standard criteria for retraction and that the 2012 refutation studies had not faithfully reproduced their growth conditions. The shadow biosphere theorist defended it to the end. Felisa Wolf-Simon has published nothing new since 2011. It is worth being careful about what that story means, because the obvious reading is the wrong one. This is not a story about a scientist who was wrong. It is the best documented case in the history of this entire research program of a testable prediction being made, tested, and answered no. The shadow biosphere generated a real hypothesis. Someone went to a lake and looked. The answer came back negative, in public, over 15 years, with everyone's name attached. That is the process working exactly as it is supposed to, and it was presented at the time as a discovery, which is the only part that went wrong. Which brings us to the version of this scenario that is no longer hypothetical. Life on Earth is homochiral. Proteins built by ribosomes use exclusively left-handed amino acids. DNA and RNA use exclusively right-handed sugars. Every organism, without exception, in every environment for 4 billion years. Nobody knows why. It is not known whether that handedness emerged before life or after it, whether life requires this particular handedness, or whether life needs to be homochiral at all. Mirror image proteins have been built in laboratories, and they function perfectly well on mirror image substrates. Electromagnetism is symmetric under reflection, so the chemistry is essentially unchanged. The weak nuclear force does break that symmetry and theoretically favors the natural forms, but by an amount nobody has shown to be large enough to matter. So a mirror biosphere is chemically permitted. And the technology to build one is closer than most people would guess. A mirror image DNA polymerase was built in 2016. Mirror image PCR followed in 2017. Mirror image transcription of inverted ribosomal RNA was demonstrated in 2022. Work toward a full mirror image ribosome has been underway since 2016. Estimates for when mirror life becomes possible run from 10 to 30 years. On the 12th of December 2024, a technical report was published titled Confronting Risks of Mirror Life. It has 38 authors, including 2 Nobel laureates, and among the signatories are George Church, Craig Venter, Drew Endy, Kevin Esvelt, and Richard Lenski. Several of them had been actively pursuing mirror life themselves and renounced the work in order to sign. Their warning is specific, and it is not the warning you would expect. A mirror bacterium would not be a better pathogen in the ordinary sense. It would not be faster, or more virulent, or better at spreading. It would be invisible. Every mechanism that constrains a normal microbe, immune recognition, predation, bacteriophages, digestive enzymes, evolved to recognize the shapes of natural-handed molecules. A mirror organism presents none of those shapes. The report's projected outcome is pervasive lethal infections in a substantial fraction of plant and animal species, including humans, and their conclusion is that such organisms should not be created without compelling evidence of safety. What happened next happened quickly. 96 biotechnology experts signed a supporting statement at a summit in 2025. The first international conference on the subject, held in Paris that year, reached broad agreement that it should not be created. The United Kingdom's Government Office for Science recommended prevention in January of 2025. Germany's Biosafety Commission issued a position that September. UNESCO's Bioethics Committee recommended a precautionary global moratorium. In 2026, the United Nations Secretary-General's Scientific Advisory Board called for defining clear red lines well before mirror life becomes feasible. Two major funders published statements declining to support the work. There is real dissent, and it deserves to be heard. Some argue the concerns are theoretical and that restrictions are premature. Ting Zhu, whose laboratory built the mirror polymerases in the first place, published an argument for guidelines that cover synthetic biological entities regardless of their handedness, and stressed the distinction between mirror molecules and mirror organisms. A letter in early 2025 argued that the immune system might in fact recognize mirror versions of certain sugars, which would weaken the evasion premise considerably. And all sides agree that mirror molecules themselves, including nuclease-resistant therapeutic aptamers already in clinical trials, are valuable and are not what is being warned about. So this scenario ranks at number 7 for a reason that is almost paradoxical. The evidence for a shadow biosphere is nil. The evidence that we would not detect one is excellent. And the only version of it we are confident could exist is the version we would have to build. If a second origin of life is sitting in a rock coating somewhere in the Mojave, the reason we have not found it is not that it is hiding. It is that every tool we own was built by the first origin to look for itself. There is one way we could still find a second sample of life. It is the one nobody wants because it would be ours. Number 6. The ones we bring with us. Every entry so far has been about something that might be out there or might have been here. This one is about something we know is here because we packed it. The scenario at number 6 is that the first extraterrestrial life humanity finds will be extraterrestrial life humanity delivered. And unlike everything above it on this list, the people who worry about this are not theorists. They are engineers, policy officers and microbiologists, and they have spent 60 years building an entire institutional apparatus around the problem, and they will tell you plainly that it is not solved. The law is older than the Apollo landings. The 1967 Outer Space Treaty, Article 9, requires states to conduct exploration so as to avoid harmful contamination and also adverse changes in the environment of the Earth, resulting from the introduction of extraterrestrial matter. That is the entire legal text on the subject. Harmful contamination. It defines no threshold, no microbe count, no measurement, and no enforcement mechanism. Every real number in this field comes instead from a voluntary scientific policy maintained by a body called COSPAR, the Committee on Space Research, which meets every 2 years and has no power to compel anyone to do anything. That policy sorts every destination in the solar system into 5 categories, and the categories are a good tour of how seriously we take each place. Category 1 is for bodies of no interest to questions of chemical evolution or the origin of life. The Sun. Mercury. There are no requirements at all. Category 2 is for bodies of significant interest, where there is only a remote chance that contamination would compromise future work. The Moon is here. Venus is here. Comets are here. The requirement is documentation. Say where you intend to land, say where you might accidentally land, and file a report if you hit something you did not mean to. Category 3 covers flybys and orbiters at places where contamination genuinely could ruin future science. Mars. Europa. Enceladus. Now you get trajectory biasing, so a dead spacecraft does not drift into the target, cleanroom assembly, active reduction of the microbial load, and an inventory of organic material if impact is possible at all. Category 4 covers landers and probes at those same places, and it splits three ways. A lander that is not looking for life is capped at 300,000 spores per spacecraft and 300 spores per square meter. That is the standard the Viking landers were sterilized to before their heat treatment. A lander that is looking for life adds stringent further requirements to protect its own samples from itself. And any component that enters what is called a Martian special region, meaning anywhere terrestrial organisms could actually propagate, is capped at 30 spores. 30. For an entire spacecraft. Category 5 is sample return, and it splits into unrestricted and restricted. Restricted return forbids destructive impact on the way home, requires containment of every piece of hardware that touched the target body, and requires containment of any unsterilized sample. Underneath all of this sits a single number, and it is the number to remember from this entry. For Category 4 missions, the requirement is a probability of forward contamination of less than 1 chance in 10,000 per mission. The Europa Clipper mission states it in its own documentation, and the definition attached to it is the part that stops you. The probability of inadvertent contamination of an ocean or other liquid water body must be less than 1 in 10,000 per mission, where contamination is defined as the introduction of a single viable terrestrial microorganism into a liquid water environment. 1 microbe. 1 chance in 10,000. That is the standard humanity has written for itself, and nobody can make anybody follow it. We have twice destroyed a working spacecraft rather than risk that number, and both cases have a shape to them worth sitting with. Galileo was flown into Jupiter on the 21st of September, 2003, after almost 8 years in orbit and 14 years of mission life, at something around 108,000 miles per hour. It had flown its entire mission with a jammed high-gain antenna, sending its data home through a backup at a tiny fraction of the intended rate, and it had endured Jupiter's radiation belts far past its design life. And the reason it had to be destroyed is the cleanest irony in this field. Galileo itself produced the strong evidence that Europa holds a saltwater ocean under its ice. That discovery is precisely why the spacecraft could not be left to drift. Its fuel was nearly gone, its orbit could no longer be reliably controlled, and a derelict wandering the Jovian system for centuries might eventually find the very moon it had made interesting. Its reward for succeeding was destruction. Cassini was flown into Saturn's atmosphere on the 15th of September 2017, while still completely functional. The propellant for course corrections was nearly exhausted. The specific body of concern was Enceladus, where Cassini had found a global subsurface ocean venting into space, with signs of hydrothermal activity at its floor. Titan is named in the mission documents too. Its final phase, called the Grand Finale, sent it through 22 orbits, threading a gap of roughly 1,500 miles between Saturn and its innermost ring, a region no spacecraft had ever entered. And in its last seconds, as it entered the atmosphere at something like 70,000 miles per hour, its thrusters fought the incoming air to keep the antenna pointed at Earth, and it kept transmitting data until it could not. Both of those are stories about doing the right thing at cost. Now the story about the framework simply not covering the case. Bereshit was built by Space IL and Israel Aerospace Industries, and it was the first privately funded attempt at a lunar landing. Its main engine failed during the braking burn, and it crashed into Mare Serenitatis on the 11th of April 2019. On board was something called the Lunar Library, assembled by a private foundation. It was a disk about the size of a DVD, built from thin sheets of nickel, holding roughly 30 million pages of text and images. It also held samples of human DNA. and it held several thousand dehydrated tardigrades in the dormant state called cryptobiosis. Picture the moment, because it is short and it is very quiet. The breaking burn stops. There is no atmosphere here to slow anything, and no sound to carry, and the lander is falling toward a plain of grey basalt that has been sterile for something on the order of 4 billion years. The impact is a single event lasting a fraction of a second. The structure fails. The nickel disc, which was engineered to survive almost anything, shears and scatters. 30 million pages of human writing and several thousand animals in dreamless suspension distribute themselves across regolith that has never held water and has never held anything alive. And then nothing happens. There is no plume to settle because there is no air. There is only a new scatter of metal on an old surface, in daylight that will last another 2 weeks, and then a night at 180 degrees below freezing, and then another day, indefinitely. Nobody has been back to look. The follow-up work is honest about the odds. Impact experiments put the tardigrade survival cutoff at roughly 0.9 kilometers per second and about 1.14 gigapascals of shock pressure, which is close to Bereshit's estimated impact conditions. The experiments suggest the animals probably did not survive. They do not prove that none did. And there is no liquid water on the moon to revive them in any case. But here is the part that belongs in this list. The moon is a Category 2 target. Documentation only. Nothing about that payload violated the policy. It was entirely legal, and the people who wrote the framework had simply never contemplated a private company putting live animals on a lunar lander. Now, how clean is a clean spacecraft? Setting aside the Viking landers, which were baked, spacecraft have typically launched carrying a spore-forming load of somewhere between 10,000 and 100,000 spores. Curiosity, which launched on the 26th of November 2011, went up with a measured total of 56,400 spores after dry heat sterilization and wiping with isopropanol. That is under the Category 4 limit. It is not under it by an order of magnitude. And the assay only counts organisms that survive a heat shock and then grow on a plate. Which returns us directly to the problem from the previous entry. The certification counts what the certification method can see. There was also an incident, and it is instructive because nothing about it was malicious. All 3 of Curiosity's drill bits were meant to remain sealed in a sterile box until they were opened on Mars by the robotic arm. About 6 months before launch, engineers worried that a rough landing could damage the drill mechanism and opened the box on the ground to mount 1 bit in the drill as insurance. Under NASA's own procedure, that box should not have been opened without the knowledge of the Planetary Protection Officer, Catherine Conley. She was not consulted. The retroactive justification was that Gale Crater was judged unlikely to contain any special regions. That is how it happens. Not through carelessness. Through a reasonable engineer making a reasonable trade against a different risk. And then there is the question of what actually lives in the rooms where we build these things. There is an organism called Tersicoccus phoenicis. When it was described, it was recognized as both a new species and an entirely new genus. It is named for the Phoenix Mars lander, in whose assembly cleanroom at Kennedy Space Center in Florida it was first found. And then it was found a second time, about 2,500 miles away, in the European launch facility at Kourou in French Guiana. 2 of the cleanest rooms human beings know how to build, on 2 different continents, harboring the same previously unknown organism, and at the time, essentially nowhere else on Earth. A finding published in 2025 added something worse. that organism enters dormancy under nutrient starvation, a viable but non-culturable state. It is the first non-spore-forming spacecraft cleanroom isolate shown to do this, which matters enormously because the certification assay is a spore assay. A non-spore former that can go dormant is a survivor the entire process is not designed to count. Also in 2025 came the larger result. 26 previously unidentified bacterial species were described from Phoenix cleanroom isolates. 53 strains across those 26 new species out of 215 sequenced genomes in work led by Junior Schultz. The conditions under which those strains were isolated read like an inventory of the ways we tried to kill them. 22 were recovered under alkaline conditions above pH 10, 8 after heat shock at 80 degrees Celsius, 7 grown at 4 degrees, 5 under an atmosphere with no oxygen at all. And the functional genomics found what you would expect if you thought about it for a moment. Genes for resistance to cleaning chemicals. Genes for forming biofilms on sterile surfaces. Genes for DNA repair and radiation protection. Genes for repairing oxidative damage. The accurate way to say this is not that cleanrooms are dirty. It is that a cleanroom is not a sterile environment. It is a selective one. And what survives one is, by definition, the hardest thing we know how to kill, pre-selected for exactly the properties that would help it survive a journey to somewhere else. In 2019, NASA convened an independent review board on all of this, chaired by the planetary scientist Alan Stern, with 12 experts. It produced 34 findings and 43 recommendations. Its core message was that guidelines written for a small number of government missions do not fit an era of private landers, cheap access to space, sample returns, and eventual human missions to Mars. It also recorded, without comment, that there is a lack of consensus as to how and when the Outer Space Treaty has legal relevance to non-governmental entities. And the case nobody has solved is the human one. A crewed vehicle carries something on the order of 100 trillion microbial cells per person and cannot be sterilized because the crew would not survive it. Europa Clipper launched on the 14th of October 2024 and will travel 1.8 billion miles to reach Jupiter in April of 2030 for 49 close flybys of Europa. Its solar arrays span more than 30 meters. There is one finding from its risk assessment that is quietly remarkable. The model met the 1 in 10,000 requirement while being essentially unaffected by how much biological material was on the spacecraft. The dominant risk terms were mission failure scenarios, not bioburden. Which is to say, the thing most likely to contaminate an ocean world is not a dirty spacecraft. It is a spacecraft that goes wrong. Some of the cleaning is done by the journey itself. Europa Clipper's route to Jupiter runs past Mars and back past Earth for gravity assists, and across those years of cruise, thermal cycling, and radiation exposure quietly reduce the biological load further than anything achievable on the ground. The spacecraft arrives cleaner than it left, because space is a better sterilizer than we are. It is also worth noting, since it will matter later on this list, that on the 18th of December 2025, that same spacecraft turned and observed an object passing through the solar system from outside it. The vehicle carrying the strictest contamination requirement ever written was, on its way to an ocean world, photographing a visitor from another star. And there is a mirror image concern that has been in the policy since the beginning and has never been tested. Restricted sample return exists because material coming the other way is also a question. Every Category 5 mission that brings back unsterilized material from somewhere we are unsure about must contain it absolutely, and must not impact on return under any circumstances. That framework has never had to hold anything, because nothing has yet been brought home from a place where the answer was in doubt. Mars sample return would be the first. So this scenario sits at number 6, because its evidence is institutional rather than astronomical, and because it is the only entry on this list where the discovery and the disaster would be the same event. Contamination is at least a problem we know we have. The next entry is about the errors we do not notice until afterward. Number 5. The signal that was always us. We are now halfway down the list, and this is the entry where the evidence becomes complete. Everything from here to number 1 rests on things that actually happened, that were measured, and whose outcomes are known. The scenario at number 5 is not that we will fail to hear anyone. It is that we will hear someone and be wrong, and the thing we heard will turn out to have been closer to the telescope than the target was. That is not a hypothetical worry. It is the entire history of the field. Every candidate signal has resolved. Not one has resolved to anyone else. And in nearly every case, the answer was an instrument, an assumption, or an ordinary piece of human machinery. Start with the founding case, because it set the standard everything since has been measured against. In 1967, a graduate student at Cambridge named Jocelyn Bell Burnell was working with a radio array on the outskirts of the city. The array was called the Interplanetary Scintillation Array. It had been designed to study how the solar wind makes distant radio sources twinkle, and she had substantially built it herself as part of her doctoral work, under her supervisor Anthony Hewish. It produced its output as ink on paper, on a chart recorder, at a rate of about 96 feet of paper every 4 days. She noticed something she called scruff, a small recurring mark that was not a source and was not interference, appearing in the same part of the sky. In total, the anomaly amounted to about 1/4 of an inch of ink in 400 feet of chart. She could have thrown it away. Instead, she went back through the earlier records, by hand, looking for the same mark in data she had already processed. She found it. On the 28th of November 1967, she resolved it into a train of pulses arriving once every 1.3373 seconds, with a regularity nothing natural was then known to produce. The object is now catalogued as PSRB 1919+21. At the time, nobody had any idea what it was. The power and the regularity briefly suggested a beacon, and the source was nicknamed LGM for Little Green Men, and then LGM1. And here is the part that matters, because it is the field's founding lesson. What killed the alien hypothesis was not skepticism or embarrassment. It was more data. Within weeks, 3 more pulsating sources turned up in completely different parts of the sky. A beacon interpretation cannot survive 4 independent sources at 4 different sky positions, all doing the same thing. They had discovered neutron stars. Hewish shared the 1974 Nobel Prize in Physics for the discovery. Bell Burnell did not, a decision that is still criticized. She received the Breakthrough Prize in 2018 and donated the entire $3 million to fund physics scholarships for students from underrepresented backgrounds. That is the template. Anomaly, restraint, more data, resolution. Now watch it run 4 more times. The best story in radio astronomy is about a microwave oven, and it is worth telling properly. There is a class of signal called a periton. Peritons are millisecond duration radio transients that sweep across frequency in a way that mimics the signature of a fast radio burst, which is one of the genuinely important astrophysical discoveries of this century. A real fast radio burst is an enormously energetic event in a distant galaxy, and its light arrives smeared across frequency because it has crossed intergalactic space. Peritons look almost exactly like that, and they come from inside the building. They were named in 2011 by Sarah Burke Spolor after a creature from a medieval bestiary, a winged stag that casts the shadow of a man. The intended sense was strangeness made by man. She found them by searching archival data from the Parkes radio telescope in Australia after the first fast radio burst had been identified, and the tell was geometry. A real burst is a point on the sky, so it appears in only 1 or 2 beams of the receiver. Her 16 signals appeared to fill the entire visible patch of sky at once, which means the source was not on the sky at all. It was local, and it was flooding the whole instrument. 46 peritons were eventually identified at Parkes between 1998 and 2015. On the 23rd of June 1998, 16 of them were detected at the same location within 7 minutes. The proposed explanations over 17 years included aircraft, lightning, solar flares, and terrestrial gamma-ray flashes. None of them fit. In December of 2014, the observatory installed a radio frequency interference monitor at the site, data that had simply never existed for the earlier events. In January of 2015, the telescope detected 3 peritons, and each one was accompanied by emission at 2.5 GHz, coming from outside the telescope's field of view. And on the 17th of March, 2015, the team reproduced peritons on demand. They did it by microwaving ceramic mugs full of water in the observatory's own kitchen and opening the microwave door before the timer had finished. It worked roughly half the times the door was opened early. The mechanism is genuinely elegant. When a magnetron shuts down, it emits a brief frequency-swept pulse near 1.4 GHz, which is close enough to a dispersion sweep to fool the pipeline. 2 microwave ovens, both still working, both more than 27 years old, were responsible for most of them. And the vindication is the part that gets left out of the joke. Once the source was identified, it became possible to demonstrate that the on-site microwaves could not have produced the original burst detected in 2001. Solving the false alarm is what confirmed fast radio bursts as real extragalactic events. Chasing down the interference is what secured the discovery. Then there is the most sensitive technosignature search ever conducted, and what it found. In 2019, the Parkes telescope, now formally named Muriang, was observing Proxima Centauri, the nearest star to the Sun, across a band from 700 MHz to 4 GHz. The pipeline flagged a narrow-band signal that persisted over 5 hours of observation, with a steady drift rate and a narrow spectral width. Those are several of the properties a genuine transmission was expected to have. The frequency was around 982 MHz. It was designated Breakthrough Listen Candidate 1, and it became public in December of 2020. 2 papers appeared in Nature Astronomy in 2021. The first, describing the overall search, was led by Shane Smith. The second, describing the analysis of the candidate itself and the method used to rule it out, was led by Sophia Sheikh. Both of them had entered the project as undergraduate summer interns. A third paper reported 39 hours of re-observation in which nothing recurred. The first paper describes the Proxima search as the most sensitive and thorough technosignature search of the nearest exoplanetary system to date, and the most sensitive technosignature search ever undertaken on any star target. The verdict was that the candidate was not a technosignature. It was identified as an electronically drifting intermodulation product of local, time-varying interferers, whose behavior happened to align with the observing cadence. Which is to say, two or more pieces of terrestrial equipment somewhere in or near the receiving chain, producing a spurious tone between them that moved in a way that matched how the telescope was moving. Breakthrough Listen's own framing was that the candidate provided an excellent test of the pipeline, and that is not a face-saving statement. The lasting product of the whole episode is the verification framework itself, the flowchart of tests a candidate has to survive before anyone says anything out loud. That framework did not exist before. It exists now because of a signal that was not real. Now the one that has not resolved. In September of 2020, Jane Greaves of Cardiff University and 18 co-authors announced the detection of phosphine in the cloud deck of Venus at an abundance of about 20 parts per billion, reported as unexplainable by any known abiotic chemistry. The work used two instruments. The James Clerk Maxwell telescope on Mauna Kea, which saw the line first, and the array called ALMA in northern Chile. The difficulty is worth appreciating. Venus is the brightest object in our sky after the Sun and the Moon. Hunting a faint absorption line against it has been described as looking for a firefly in front of the Sun. And the relative motion of the two planets introduces Doppler shifts that have to be filtered out before you can see anything at all. The trouble started with the array. It is not designed to observe a target that bright, and the data had to be recalibrated. A reanalysis published shortly afterward argued that the apparent line could be a spurious feature produced by the calibration itself, and that the original fitting method leads to severe overestimation of the significance of spectral features. A separate team argued the line might be sulfur dioxide instead, and ended their abstract by suggesting the original paper be retracted. That was widely regarded as excessive, and the team later agreed the sentence was inappropriate and apologized. The number correction is the real story. After recalibration, phosphine was recovered at about 5 sigma, but with a localized abundance peaking at 5 to 10 parts per billion, and a planet-averaged abundance of 1 to 4. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. The molecule did not vanish. It shrank by most of an order of magnitude. And the original group kept working, which is what makes this the unresolved case rather than the closed one. A second observing round in the summer of 2020 saw phosphine again, with a different instrument on the same telescope. A large monitoring program was awarded 200 hours of telescope time and reported the molecule again in February of 2022 and in May of 2023. And a separate group went back to mass spectrometer data collected in the Venusian atmosphere by an American probe in 1978 and found something consistent with phosphine in a 40-year-old dataset. Other groups report non-detections and upper limits. A review published in 2024 is titled "Without Ornament, Source of Phosphine on Venus, an Unsolved Problem." And it should be said clearly that even a confirmed detection would not be life. Volcanism is a live alternative, and papers arguing both for and against it have appeared in the same journal. Our best surface maps of Venus are still from a mission that finished in 1994. One disarming detail, because it is true. Greaves used a picture of a penguin in her talks because phosphine is found in penguin digestive tracts. It became a small internet joke, and she has since publicly clarified that she was not proposing flying Venusian penguins. Which brings us to the current one. K218b is a planet 124 light-years away, orbiting a red dwarf every 32.94 days. It is 2.61 times the radius of Earth and 8.63 times the mass, which gives it a density between Earth's and Neptune's. It was discovered in 2015. Its properties are what led to the definition of an entire proposed planet class, the Hycean worlds, meaning abundant liquid water beneath a hydrogen envelope. In 2019, it produced the first detection of water vapor on a planet that was not a hot giant, and that was major news. Later work questioned even that, with one group suggesting the signal was stellar activity and another arguing the water evidence was actually methane. In September of 2023, Niku Madhusudan and colleagues at Cambridge reported detections of methane and carbon dioxide from the James Webb Space Telescope, plus a tentative hint of dimethyl sulfide. That last molecule is the interesting one, because on Earth it is produced essentially only by marine microorganisms. In April of 2025, the same group reported mid-infrared data consistent with dimethyl sulfide, or a related sulfur compound, at 3 sigma. 3 sigma means roughly a 0.3% chance of the data fitting by coincidence. The bar for a claimed detection in physics is 5 sigma, which is about 6 parts in 10 million. NASA did not issue a press release. On the 18th of April 2025, the agency instead issued a statement reiterating that follow-up studies and multiple converging lines of evidence would be needed to confirm a true biosignature and rule out false positives. The reanalyses arrived within weeks. One showed that despite a claimed 3.4 sigma deviation from a flat line is an acceptable fit to the data. Another independently questioned the statistical robustness. And the most thorough, the first joint analysis of the full spectrum from 0.6 to 12 microns, using 3 independent data reduction pipelines and 2 retrieval codes, concluded that there is no statistical significance for those molecules in the planet's atmosphere. They found the marginal preference was an artifact of limiting how many molecules the model was allowed to consider in the first place. 2 of their numbers are worth keeping. Using the best-fitting model on the published data, about 25 more transits would be needed to reject a flat line at 3 sigma. And under an alternative choice of how to bin the data, 87.5% of retrievals do not support the detection at all. A further reanalysis concluded that red noise, not an astrophysical signal, plagues the mid-infrared data. Then, in July of 2025, came a NASA-led synthesis, led by Renyu Hu at the Jet Propulsion Laboratory, with Madhusudan and other independent teams participating. They added 4 new transits and had 3 separate teams, each develop their own interpretation rather than agreeing on one model in advance. Methane and carbon dioxide were conclusively detected. The dimethyl sulfide signal did not vanish. It weakened to about 2.7 sigma. And that same work produced the finding that actually settles what a detection would mean. Abiotic photochemistry alone can produce detectable dimethyl sulfide and other organosulfur molecules in hydrogen-rich atmospheres. Hu's own line was that this means the molecule, on its own, may not be a definitive sign of life on this planet. Laboratory experiments in 2024 demonstrated the same thing under simulated conditions. And the molecule has been detected in comets and in interstellar clouds, where there is no biology of any kind. Madhusudan's counter is fair and belongs in the record. He argues that whether it is a reliable biomarker depends on how deep the atmosphere is. A deep atmosphere gives you roots to make it without life. A thin atmosphere over a liquid ocean, he maintains, leaves biology as the only currently known explanation. Where it stands is this. Methane is solid. Carbon dioxide is likely. Dimethyl sulfide is not established, has been rejected as statistically insignificant by multiple independent reanalyses, and would not by itself indicate life even if real. A modeling paper in 2026 supports an interpretation with no dimethyl sulfide at all and finds no strong evidence for a water-rich interior, which is in direct tension with the 2025 synthesis. The question is genuinely open, and the honest position is that we do not know what that planet is. There is one more false positive worth naming, and it is the one that has not happened yet. Molecular oxygen is the flagship remote biosignature. It is reactive. It should not persist without something making it, and on Earth, it is made by life. The problem is that there are now several known ways to accumulate a great deal of it with no life at all. Water can be split by ultraviolet light, and the hydrogen can escape to space, leaving oxygen behind, on a lifeless world entirely covered by ocean, where there is no exposed rock to soak it back up. Carbon dioxide can be split the same way on rocky planets around small stars. And red dwarfs go through extended superluminous youths, during which ultraviolet-driven hydrogen loss could leave a habitable zone planet with hundreds to thousands of bars of oxygen produced by nothing but physics. Even a single stellar flare can shift the photochemistry enough to matter. There are discriminators. The presence of carbon monoxide and a particular absorption feature produced when oxygen molecules collide in pairs are the telltales that separate the abiotic case from the biological one. But the general lesson is the one that ties this whole entry together, and it applies as much to a spectrum as it does to a radio pulse. No single gas is a biosignature. Context is the biosignature. The star, the planet's history, and what else is and is not in the data. In every resolved case on this list, the thing that produced the false signal was closer to the telescope than the target was. A microwave oven in the kitchen. An intermodulation product in the receiver chain. A calibration routine. A model with too few molecules in it. That is what the record actually shows, and it is why this scenario ranks in the middle rather than at the bottom. Its evidence is complete. Every one of those searches was pointed outward, at stars. There is one place, much closer, that nobody has ever pointed a radar at all. Number 4, the ones that might already be here. The idea at number 4 is older than Radio SETI, and it has a peculiar quality. It is the only entry on this list that could be settled cheaply, this decade, with equipment we already own, and nobody has ever done it. It begins in Nature, on the 28th of May, 1960. 2 months before Frank Drake pointed a dish at his first star, an Australian physicist named Ronald Bracewell published a short paper called Communications from Superior Galactic Communities and made an argument that has never been answered. His argument was economic. If you are an advanced civilization trying to make contact with emerging species, radio is a poor way to do it. It is expensive to broadcast across interstellar distances. You must broadcast continuously for millennia in the hope that someone is listening, and even if it works, your conversation runs at a round-trip delay of decades or centuries. Every exchange takes longer than a human lifetime. The alternative is to send a machine. Place an autonomous device in the target system and let it wait. It can monitor the biosphere continuously across geological spans. It can report home at leisure, and when the local species crosses some threshold, large-scale radio, say, or interplanetary flight, it can begin a conversation at conversational speed. This became known as the Sentinel hypothesis, and such a machine is now called a Bracewell probe. The advantage is decisive, and it does not go away. A probe that is already here permits a real-time conversation. Nothing sent by radio ever can. The obvious objection is that if such a thing were here, we would have found it. which is where the modern version of the argument comes in, and it is more specific than you would expect. In September of 2019, James Benford published a paper in the Astronomical Journal titled "Looking for Lurkers." Benford is an independent plasma physicist working out of a small company in Lafayette, California. He does not hold a university post. The work was funded by the Breakthrough Foundation. His definition is direct. "I will call such a probe a lurker," he writes, "a hidden, observing probe which may respond to an intentional signal and may not, depending on unknown alien motivations." And his contribution is not the idea, it is the address. He argues that if you wanted to park something to observe Earth for a very long time, there is one particular neighborhood that is better than any other, and it is a neighborhood almost nobody has looked at. The neighborhood is co-orbital space. These are objects that share Earth's orbital period around the Sun, without orbiting Earth itself. They travel with us. In his phrase, they provide materials, a firm anchor, and concealment, all at once. He is systematic about rejecting the alternatives. Earth orbit is unstable, so anything there decays or drifts within decades without active station keeping, and in his words it would be very observable, and I suspect they wouldn't want to be seen too soon. The Moon has been imaged at roughly 1 meter resolution across almost its entire surface, and besides, if a probe were going to respond to us, it would surely have done so by now. The asteroid belt is better for concealment, and much better for long-term orbital stability, on the order of hundreds of millions rather than tens of thousands of years. But the sunlight there is reduced by a factor of 4 to 11, which forces nuclear power, and the cold degrades mechanical and chemical systems over long timescales. Co-orbital objects, by contrast, approach us annually at distances shorter than anything except the Moon, and remain stable for centuries to hundreds of thousands of years. His proposal is a 5-step observing program, and it is the most practical thing on this entire list. First, a multi-year optical and radio campaign measuring size, shape, rotation, and spectra out to at least 1.2 microns, watching specifically for specular reflection, the mirror-like glint you would get off a manufactured surface rather than off rock. Second, passive listening. Third, active planetary radar. And here, he makes a factual observation that is genuinely surprising. These objects, he writes, have not been pinged or imaged by any planetary radar as yet. Fourth, radar and listening simultaneously. Fifth, robotic and crewed inspection. He also disposes of the usual ethical objection to transmitting. This does not incur the objections to sending interstellar messages, he writes, because any such alien lurkers would already know we are here. And his suggested opening message is 1 line long and rather good. A high-resolution photograph of the object itself. "We see you." To his credit, he states the claim in falsifiable form. There exist in near-Earth space extraterrestrial probes which are observing Earth, and it may be possible for us to find and contact them. And there is a reachability argument underneath it. At 1/10 of light speed, a probe crosses 100 light-years in about 300 years. There are roughly 3,000 main sequence stars within that radius. For a civilization that thinks in millennia, this is not an exotic proposition. It is a delivery route. So what is actually out there? The best-studied object is called Kamo-O'Alewa, discovered on the 27th of April 2016 by the Pan-STARRS survey at Haleakala Observatory on Maui. Its name comes from a Hawaiian creation chant and means, roughly, the oscillating fragment. Its orbit is the strange part. It runs between 0.9 and 1.1 astronomical units from the Sun, with a period of about 366 days, and it alternates between two configurations on timescales of about 10,000 years. In a rotating reference frame that turns with Earth, it appears to trace an ellipse around us, completing a loop roughly every 45 years. It has been doing this for a very long time and will keep doing it as a stable companion for somewhere between 300,000 and 500,000 years. It never comes close. It stays between 38 and 100 lunar distances away. Its closest recorded approach was on the 27th of December, 1923, at about 12.4 million kilometers. And it spins fast. Once every 28 minutes. That matters more than it sounds, because there is a well-established spin barrier at around 2.5 hours, below which a loosely bound pile of rubble simply flies apart. Anything rotating faster than that has to be held together by something more than its own gravity. So this object is likely a monolith. A single solid rock or a small number of chunks. In November of 2021, a team at the University of Arizona, led by Ben Sharkey, with Vishnu Reddy and Renu Malhotra, published spectroscopy from the Large Binocular Telescope and the Lowell Discovery Telescope, arguing that its surface material matches weathered lunar silicate. That it is, in other words, a piece of the moon. The case rested on four things: an Earth-like orbit, proximity to the Earth-Moon system, a spectrum redder than typical asteroids, and a similarity to space-weathered lunar material. In April of 2024, a Chinese-led team went further and named a source. Giordano Bruno, a crater about 22 kilometers across, on the lunar far side, young enough and the right size. Their own arithmetic was modest about it. The impact would have produced roughly 300 fragments of the right size, of which a best case of about 3 might have ended up in Earth's co-orbital space. And then, this year, the story reversed. A team spanning the European Space Agency's Near-Earth Object Center, Belgrade, Helsinki and Luleå, ran Monte Carlo integrations of 100,000 orbits and folded the results into population models for near-Earth asteroids. They found roughly 1.2 expected objects like this arriving from the main asteroid belt, against 0.04 from Giordano Bruno ejecta. More than an order of magnitude apart. Their conclusion was that the population can be explained without relying on the lunar origin hypothesis at all. They also pointed out that the crater's own measured spectrum shows absorption features and no steep red slope, which is close to the opposite of what the object shows. Their preferred alternative is that laser-irradiated ordinary chondrite powder reproduces that red slope in the laboratory. So this may simply be a main belt asteroid with unusually extreme space weathering. Then the James Webb Space Telescope looked at it in February of 2026, and the results were published in July. The diameter came down to 18 meters, plus or minus 2. The ground-based estimates had ranged from 40 to 100, and the best-fit geometric albedo came out at 0.59. The Moon's geometric albedo is about 0.12. It is roughly 5 times too bright to be lunar highland or mare material. Its near-infrared spectrum is more neutral than the 2021 ground-based data suggested, aligning instead with ordinary silicate asteroid classes. Mikael Granvik, one of the researchers on the population modeling side, put it plainly in June of this year. "If you just take the size of this body," he said, "it is very weird that it would be so large and have been ejected from the Moon so recently." His models put it about 10 times more likely to be from the inner main belt. Both sides agree that only a returned sample settles it, because space weathering makes chemically distinct objects look alike from a distance. That is the same trap that produced a decades-long puzzle about asteroid compositions, which was only resolved when a spacecraft brought grains home from a small asteroid and let people put them under a microscope. And that is exactly what is happening right now. Tianwen-2 launched on the 28th of May 2025 from the Xichang Satellite Launch Center on a rocket that had never before put a payload directly onto an escape trajectory from Earth. It runs on solar electric ion propulsion. It detected its target optically on the 6th of June 2026. It performed its insertion burn on the 7th at about 30,000 kilometers. It closed to about 2,000 kilometers by the 19th of June and then took up station keeping at roughly 20 kilometers. So picture where we are at this moment. There is a rock 18 meters across, tumbling once every 28 minutes, brighter than any surface on the Moon, that has been looping around this planet every 45 years for hundreds of thousands of years. It was discovered 10 years ago. Until then, nobody knew it existed. And 20 kilometers off it, holding position, there is a spacecraft. It carries 11 instruments, including an imaging spectrometer, a thermal radiation spectrometer, a magnetometer, an ejector analyzer, and a sounding radar. Its survey plan will bring it down through 20 kilometers, then 3, then 600 meters, then 300. It will use explosives to expose material beneath the surface. It will attempt 3 different sampling methods, one of which, anchoring itself to the surface with 4 robotic arms tipped with drills, has never been done on an asteroid before. The radar has not been switched on for the purpose Benford had in mind. Nobody involved is looking for a probe. They are doing planetary science on a small rock for entirely ordinary reasons. But the instrument that Benford asked for in 2019 is now parked 20 kilometers from the object he named, and it got there for reasons that have nothing to do with his argument at all. The mission is planned to depart in April of 2027, with a sample capsule landing in Inner Mongolia in late November of that year, entering the atmosphere at 12 kilometers per second. The target is at least 100 grams. For scale, a previous mission returned about 1,500 micrograms from one asteroid, another returned 5.4 grams, and an American mission returned 121.6 grams from a third. After the sample is released, the spacecraft continues on to a comet in the main belt, arriving in January of 2035. Now, the reason this scenario ranks where it does, rather than lower, is a genuine blind spot in the sky survey. There are more than 37,000 known near-Earth asteroids. Above 1 kilometer in size, we have found about 911 out of an estimated 981. That is essentially complete, and it was a deliberate achievement mandated by the United States Congress and delivered by 2011. Below that, completeness collapses fast. Above 140 meters, only about 44% of an estimated 35,000 objects had been found by the end of 2022. Above 40 meters, roughly 1.3% of an estimated 840,000. And above 3.5 meters, about 0.003% of an estimated 400 million objects. There is also a structural gap. Most near-Earth object surveys cannot see anything approaching from the direction of the Sun at all. Ground surveys need dark sky, and even space telescopes avoid pointing near the Sun to protect their optics. Dedicated infrared missions are being built specifically to close that gap. And sizes themselves are soft, in a way this entry has already demonstrated. Most diameters are derived from brightness, plus an assumed reflectivity, usually around 14%. Individual diameters are uncertain by more than a factor of 2, and volumes by a factor of 8. Real reflectivity ranges from 5 to 30%. which is precisely how one object's estimated size fell from 100 meters to 18 the moment a better instrument looked at it. But the gap is closing. Simulations of survey performance put the Vera Rubin Observatory at 90% completeness for objects in this class by 2030. The population Benford wanted searched is about to be catalogued whether anyone is interested in his argument or not. There is a cautionary tale attached to this entry, and it belongs here rather than being left out, because it shows what the same instinct looks like without the discipline from the previous entry. The Galileo project was announced in July of 2021 at Harvard, co-founded by Avi Loeb. Its stated scope limits are sound. Only known physics explanations are in scope, and it will not engage in retroactive analysis of existing images or radar data. It has built real hardware, including an all-sky infrared array using 8 uncooled long-wave cameras, a passive radar network, an acoustic array, and optical all-sky cameras. Its first science results paper, published in 2025, reported roughly 500,000 reconstructed trajectories across a 5-month commissioning period. About 16% were flagged as outliers, and of roughly 80,000 outliers, 144 remain ambiguous, described in the paper's own words as likely mundane objects. 0 confirmed anomalies. That is a normal, honest instrumentation result. The Pacific expedition is the part that went wrong. A fireball on the 8th of January 2014 near Manus Island in Papua New Guinea was catalogued at 44.8 kilometers per second, which would make it interstellar. In June of 2023, a towed magnetic sled survey recovered about 700 tiny spherules from the seafloor, and analysis of 47 of them found an unusual composition, enriched in beryllium, lanthanum, and uranium, in 5. The response was comprehensive. Independent analysis showed no statistical spatial correlation between the spherules and the fireball, that ion isotope ratios indicate a solar system origin with greater than 99.995% probability, that the lanthanum and uranium enrichments had been seen in micrometeorites before and attributed to terrestrial contamination, and that the beryllium abundances are what you get from seafloor nodules after long exposure to seawater. A separate note concluded the samples were consistent with coal fly ash. And then there is the truck. A 2024 study of the seismic and acoustic records found that the seismic signal used to localize the search area was spurious. Its polarization, they wrote, is indicative of a vehicle traveling up the road toward the seismometer, pausing in the vicinity of the hospital before heading back in the reverse direction a few minutes later. They found hundreds of similar tremors in the surrounding weeks, several per hour, almost always between 5 in the morning and 11 at night. The acoustic best fit location for the actual fireball sits about 170 kilometers from where the search was conducted. And the interstellar velocity itself is disputed, with independent work concluding the high value was most probably a measurement error. Both things are true at once, and that is why they belong in the same entry. Benford's proposal is a cheap, falsifiable, entirely reasonable observing program that nobody has run. The Pacific expedition is what the same instinct looks like when it skips the verification framework that the previous entry spent 5 decades building. The strongest thing that can be said for this scenario is not that a probe is there. It is that in 66 years since Bracewell proposed it, nobody has ever aimed a radar at the places where it would be. And now, for reasons that have nothing to do with the question, someone finally has. A probe in our own orbit would be a visitor that stopped. The next entry is about visitors who do not stop, and about what their speed would do to our sky. Number 3, the front. The entry at number 3 contains the single best idea on this list. It is not the most likely scenario, and it is not the one with the most evidence. But it contains one argument that, once you have understood it, changes what the emptiness of the sky is allowed to mean. To get there, we need a piece of reasoning from 1983, and it starts with a coincidence. Brandon Carter, who coined the term anthropic principle, published a paper that year in the Philosophical Transactions of the Royal Society. He noticed that two numbers agree when they have no reason to. The age of the Earth when intelligent life appeared on it is about 4.5 billion years. The total main sequence lifetime of the Sun is about 10 billion years. Those figures agree within a factor of 2. And Carter's point was that they should not. One of them is set by biology and geology. The other is set by nuclear physics in the core of a star. In his words, they have nothing directly to do with each other, and there is no a priori reason for predicting such a close observational coincidence. His resolution was uncomfortable. If intelligence typically takes much less time than a star's lifetime, we should have appeared early, and the numbers would not match. If it typically takes much longer, then we exist only because of a fluke, and the fluke would push us right up against the deadline, which is exactly what we observe. He chose the second. The mechanism he proposed is called hard steps. Evolution has to pass through a series of intermediate stages. Most of them are easy, meaning they happen with near certainty once conditions allow. But some are hard, meaning the average waiting time for them is comparable to or longer than the entire lifetime of the star. The mathematics of this is straightforward, and it has a specific shape. The probability of completing a number of equally unlikely steps within a given time follows a power law, where the exponent is the number of hard steps. And the exponent controls where in the available window the last step tends to land. With 1 or 2 hard steps, you finish comfortably. With 3 or more, you finish right at the edge. Carter's own estimate was 1 or 2. His candidates were the origin of the genetic code and what he called the final breakthrough in cerebral development. He revised it himself in 2008 to 5 hard steps if evolution was exclusively terrestrial, or 6 if, as he then thought plausible, the first step happened on Mars. Later work proposed 10 candidate steps, with 3 criteria for what qualifies. The step must be unique in the history of life. The trait must involve many genes. And it must be essential for intelligence. A 4th criterion was added afterward. The hard steps should be roughly evenly spaced through Earth's history. Now to the model that uses it. In September of 2021, Robin Hanson, Daniel Martin, Calvin McCarter, and Jonathan Paulson published a paper in the Astrophysical Journal with the title, "If Loud Aliens Explain Human Earliness, Quiet Aliens Are Also Rare." The simulation code is public. And Hanson is the same person who, 2 years earlier, co-authored the rebuttal to the sleeping civilizations argument at number 10. Their taxonomy is the first useful thing. To a first approximation, they write, there are 2 kinds of aliens: quiet and loud. Loud, or expansive, aliens expand fast, last long, and make visible changes to their volumes. Quiet aliens fail to meet at least one of those criteria. They then define the loud kind formally, and the definition is the model. A grabby civilization expands its controlled volume at some common speed, clearly changes the appearance of what it controls, appears according to a power law in time, but never inside a volume someone else already holds, and does not die unless displaced. Note what that excludes. This model explicitly rejects the idea that they are hiding. A grabby civilization, by construction, does not hide. 3 free parameters, each of which they argue is estimable to within roughly a factor of 4. The expansion speed, and the constant and the power of the law describing how often they appear. The power comes from the hard steps literature about Earth's own history. They take 6 as their conservative middle estimate, considering 3 to 12 as the plausible range. The constant comes from treating our own date, 13.8 billion years after the Big Bang, as a random sample from the distribution of possible alien appearance dates. And the speed comes from the sky being empty, which is where the good idea is. Here is the argument, and it is worth going slowly because it is genuinely counterintuitive and it does not survive being rushed. Suppose a civilization expands outward from its home system at some fraction of the speed of light. Suppose it visibly alters what it controls so that its volume looks different from the outside. Now ask what you would see standing outside that volume as it approaches you. You would see it by light, and light travels at exactly 1 speed. So the news of its expansion travels toward you at light speed, and the front itself travels toward you at whatever fraction of light speed the civilization manages. If they expand slowly, at a few percent of light speed, then the light announcing their arrival gets to you enormously earlier than they do. You would have millions of years of warning. You would look up and see an altered region of sky, growing. But if they expand at close to light speed, the warning barely outruns the event. The light gets to you shortly before they do. And in the limit, you see nothing at all until they are already here. The paper's own statement of this is precise. If their expansion speed were within 25% of light speed, a selection effect implies that we are less likely to see than to not see such volumes. Thus, if we could have seen them, they would be here now, instead of us. If their speed were much lower, we would almost surely see them. Read that again, because of what it does to the last 60 years of this discussion. The emptiness of our sky is not evidence that nobody is expanding. It is evidence about how fast anyone expanding is moving. Slow expansion would be visible, and we do not see it. Fast expansion would be invisible right up until the moment it stopped being a question. The sky being empty is therefore consistent with 2 situations, and the model cannot distinguish them from the outside. Either nobody is doing this, or everybody doing it is doing it fast. Their conclusion from that reasoning is that aliens, if they expand at all, expand at over half the speed of light, and that speeds below a third are greatly disfavored. And then the third result, which is the one the paper is really about, and it has nothing to do with aliens directly. Only about 8% of the interstellar gas in the universe has been turned into stars so far. 95% of stars last longer than our sun. Some last roughly 2,000 times longer. Small red stars burn their fuel so slowly that the maximum stellar lifetime, down to the smallest object that can sustain hydrogen fusion, runs to something like 20 trillion years. The universe is 13.8 billion years old. It has a habitable future measured in the trillions. We are, on any reasonable accounting, at the very beginning of it. So the question the paper actually poses is not why the sky is quiet. It is, why have we humans appeared so early in the history of the universe? And their sentence on this deserves to be heard exactly as written. Our percentile rank is always below 1% for maximum lifetimes beyond 1 trillion years, no matter what the values of other parameters. Even under punishing restrictions, the number barely moves. At a power of 6 with a maximum stellar lifetime of only 10 billion years, all percentile ranks stay below about 10.6%. We are early, not marginally, not arguably. By the model's own accounting, We are in the first 1% of the window, and no adjustment of the assumptions rescues it. And the grabby aliens model exists to explain that. Its answer is that we had to appear near now, because later would be too late. If expansion fronts fill the universe over the next few billion years, then the window in which an independent civilization can arise at all closes. We are not early by luck. We are early because early is the only time this happens. Hansen preempts the obvious objection about small stars, and he is honest about how much work it has to do. Merely favoring higher mass stars by large factors, he writes, is not sufficient to solve the puzzle. One must instead do something closer to eliminating low-mass stars entirely from consideration. You cannot fix the earliness problem by saying red dwarf planets are bad places to live. You have to say they are impossible places, all of them, everywhere. Some further numbers follow from the model. On average, at the moment a grabby civilization appears, between a third and a half of the universe is already inside someone else's volume. Once a volume is taken, it stays taken and permanently looks different. The median origin date for grabby civilizations is later than the present, meaning we are early, even among the early. And when we would encounter one, in the middle scenario, works out to somewhere between roughly 500 million and a couple of billion years from now. There is one figure in the paper that puts our position in perspective. Our galaxy has around 100 billion stars, against an average of about 100 million for galaxies generally, which means the Milky Way counts as roughly 1,000 average galaxies. The paper's own summary of what that implies is one line long. We apparently live on a 1 in a million galaxies rare Earth. And the darkest result is worth stating flatly, because it is the reason people argue about this paper. If grabby civilizations arise from ordinary non-expanding ones, then to expect even one other ordinary civilization ever active in our galaxy requires a transition chance below about 1 in 10,000. For one active in our galaxy right now, below 1 in 10 million. Hansen's own gloss on this is short. Such low chances would bode badly for humanity's future. Now the rebuttal, and it is not a quibble. It is an attack on the foundation. In February of 2025, Daniel Mills, Jennifer McAlady, Adam Frank, and Jason Wright published a paper in Science Advances titled A Reassessment of the Hard Steps Model for the Evolution of Intelligent Life. Frank is the same astrophysicist who co-wrote the Silurian hypothesis at number 8, which is a small demonstration of how few people work on these questions. Their core argument is that Carter used the wrong clock. In their words, the hard steps model famously ignores perhaps the prime determinant of macroevolutionary timescales on Earth, which is the Earth system itself. Carter assumed the biosphere remains viable until the Sun leaves the main sequence, 5 billion years from now. But Earth system modeling says otherwise. As the Sun brightens, the carbon cycle draws down atmospheric carbon dioxide, and complex life ends through carbon starvation or through runaway warming, somewhere on the order of 1 to 1.9 billion years from now. Not 5. Which changes the coincidence entirely. Our appearance goes from representing about 50% of the allotted time to about 70 or 80%. And their alternative explanation is that the delay in the appearance of humans is not a series of improbable accidents at all. It is the sequential opening of new global environmental windows, with humanity arising relatively quickly once the right conditions were established. In their phrase, we evolved neither early nor late. We evolved on time. The mechanism they propose is what they call a permissive environment. Environmental change, they write, does not itself cause or explain the evolutionary innovation in question, but instead represents the removal of an external constraint that had previously prevented it. And their case is oxygen, and the numbers are the most quietly startling on this list. The atmosphere was without free oxygen until the Great Oxidation Event, 2.4 to 2.2 billion years ago, when it irreversibly exceeded 1,000% of present levels. It did not stabilize near modern values until the Paleozoic Oxygenation Event, 420 to 400 million years ago, which means up to 52% of Earth's history elapsed before atmospheric oxygen stabilized above trace amounts, and up to 91% elapsed before it stabilized near modern levels. Then they apply it to us. The lower oxygen limit for long-term human habitation is estimated at 53 to 59% of present levels, which has only been reliably available for the last 400 million years. Earth's atmosphere, they conclude, has only been conducive to long-term human habitation for the last 9% of its history. Not 100%, as Carter assumed. And there is a final number that is the best single fact in the paper. Open-air ignition and maintenance of combustion requires at least 87.8% of present oxygen levels. Fire needs more oxygen than a human body does. Which means there was an interval on this planet, and by implication on many planets, during which a species could breathe and think and build and could not light a fire. No smelting. No ceramics beyond what a lightning strike gives you. No steam. No industry of any kind. Not because they lacked ingenuity, but because the air would not carry a flame. They also dissolve the apparent uniqueness of the hard steps in two ways that do not require improbability. The first is information loss. Between 50 and 75% of lineages that independently evolved some repeated innovation contain 5 or fewer species, which means independent origins routinely vanish from the record without leaving a trace. Their illustration is precise. One amoeba lineage acquired photosynthetic machinery from a distinct bacterial ancestor only 90 to 140 million years ago. The ancient version of that same event, more than 1 billion years ago, produced descendants including over 19,000 microbial species and more than 500,000 land plants. Both events happened. Only one of them looks unique. The second is priority. The first lineage through a door occupies the niche and blocks anyone else from repeating the trick. They cite one experiment that is genuinely surprising. Yeast grown in clusters at 0, 27, and 72% of present oxygen grew larger under no oxygen at all and under 72%, but stalled at 27. Which raises the possibility that the low but not zero oxygen of the middle of Earth's history actively suppressed multicellular animal life for 1 billion years, rather than merely failing to permit it. Their predictions are testable, which is the point. If the origin of life is genuinely a hard step, atmospheric biosignatures should be rare among Earth-like planets. If their model is right, spectra resembling Earth at various stages should be common or even universal, with a planet's age determining which one you see. And if there are no hard steps at all, technosignatures should be common on Earth-like planets of sufficient age. They are also careful. We do not claim to have successfully falsified the hard steps model, they write, but we do claim to have formulated a justifiable and testable alternative to it. This is a live disagreement between named people who are all still working. Hansen's model requires a high number of hard steps. Mills and his colleagues argue the number may be 0. And if they are right, the earliness puzzle largely evaporates, and the grabby alien's explanation loses the thing it was invented to explain. There is an older version of this whole argument underneath it, and it is worth a moment because it shaped policy. In September of 1980, Frank Tipler published a paper titled, "Without Hedging, Extraterrestrial Intelligent Beings Do Not Exist." His argument was that any species capable of interstellar communication would necessarily develop interstellar travel, and that this would lead to the colonization of the galaxy in less than 300 million years. The vehicle was a self-reproducing machine that finds raw material in asteroids and comets and builds copies of itself. His cost estimate was about $30 billion, which he compared to the Apollo program. And his bottleneck was not propulsion. "It is a deficiency in computer technology," he wrote, "not rocket technology, which prevents us from beginning the exploration of the galaxy tomorrow." Michael Hart had made the same argument in 1975 and concluded that searching was probably a waste of time and money. Senator William Proxmire cited that reasoning when he cancelled NASA's SETI funding in 1981, and Congress cancelled a second effort in 1993. An argument about hard steps closed a research program twice. Carl Sagan and William Newman answered in 1983. Their counter was that Tipler had underestimated his own replication rate, and that such machines should already have consumed most of the mass in the galaxy. Any intelligent species would therefore not build them, and would destroy any it found. Their conclusion was that there is no galactic empire. And their analogy is the best line in the exchange. It is possible to walk across Rome in a day. But Rome was not built in a day. More recent work has softened the whole thing considerably. A 2019 study introduced what its authors called the Aurora effect, after a Kim Stanley Robinson novel, which simply allows that good worlds are hard to find. Formerly habitable is not the same as settleable. Their conclusion is the important part. These results, they write, break the link between the observation that there are no interstellar visitors on Earth now and the conclusion that humans must therefore be the only technological civilization in the galaxy. And there is one older objection that no model has answered, from the paleontologist Stephen Jay Gould, and it deserves to close this entry. "I must confess," he wrote, "that I simply don't know how to react to such arguments. I have enough trouble predicting the plans and reactions of the people closest to me. I'll be damned if I can state with certainty what some extraterrestrial source of intelligence might do." At number 8, we talked about a few centimeters of sediment holding an entire industrial era. This entry is the same measurement taken along a different axis. If expansion happens at close to light speed, then the interval in which anyone is visible before they arrive is a sliver of the same kind. Thin in time rather than thin in rock, and invisible for the same reason, because everything interesting is compressed into a layer too narrow to read. If the speed argument is right, then the sky being empty tonight tells us almost nothing about whether it will be empty tomorrow. And the only reason we are here to ask is that nobody has arrived yet. That argument is entirely theoretical. But 3 objects have already crossed this solar system from outside it, and one of them is older than the Sun. Number 2, the things passing through. Until 1992, panspermia was philosophy. The idea that life, or its chemical precursors, could move between star systems inside rock was a respectable speculation, with no way to test it, because nobody had ever seen anything arrive from outside. Then, in 2017, something did. Then, 2 years later, something else. Then, 6 years after that, a third. And in the 8 years those 3 visits took, an argument about origins turned into an argument about measurement. The first was designated 1I, 2017 U1, and named Oumuamua. It was found on the 19th of October, 2017, by Robert Werrick, working with the Pan-STARRS telescope at Haleakala Observatory in Hawaii. By the time anyone saw it, it was leaving. It had passed its closest point to the Sun 40 days earlier, on the 9th of September. When first observed, it was already 33 million kilometers away and outbound. Its closest approach to Earth had been 24 million kilometers, 5 days before it was discovered. Its speed relative to the Sun, out in interstellar space, was 26.33 kilometers per second, both before it arrived and after it left. That is roughly 95,000 kilometers per hour. It came from roughly the direction of Vega, and its approach vector was 6 degrees off the solar apex, which is the direction the Sun is moving, and therefore the most likely direction for something to arrive from. Its velocity is very close to what astronomers call the local standard of rest, the average motion of the material around us, which rules out the dozen nearest stars as its origin and suggests it may have been circling the galaxy for a very long time. And this is the part that has to be stated clearly, because almost everything written about that object obscures it. Its shape and size were never measured. It was never anything more than a point of light, even in the most powerful telescopes on Earth. Everything we say about it comes from the light curve, which is to say from how its brightness varied as it turned. That variation was large, which means the object is not round. It is either a highly elongated cigar or an extremely flattened disk. Assuming a reflectivity of 10%, its dimensions come out somewhere between 100 and 1,000 meters along its long axis. Modeling work found a disk slightly more likely than a cigar, because a disk produces the observed brightness range without requiring that we happen to be looking at it from a special angle. It was tumbling, not spinning about a fixed axis. The genuine anomaly was that it accelerated. Reported in June of 2018, a non-gravitational push near perihelion added about 17 meters per second to its velocity. Comets do this all the time because the ice on their surface turns to gas in sunlight and acts as a thruster. But comets that do it have tails. Oumuamua had no observable tail and no coma. Infrared observations set a tight limit on carbon-based outgassing and indicated it was at least 10 times shinier than a typical comet. That is what generated the famous proposal in late 2018 that it could be an artificial thin sail pushed by sunlight. The counter-arguments were prompt. The evidence was insufficient to support the premise, and a tumbling sail cannot sustain a net push because it spends as much time facing the wrong way as the right way. One natural explanation, offered in 2021, proposed a fragment of nitrogen ice chipped off the surface of a Pluto-like body, which would sublimate invisibly and could lose 92% of its mass in a month, sculpting an ordinary shape into an extreme one. The objection was that the required galactic supply of nitrogen ice is implausibly large. The leading explanation now is a different one, published in Nature in March of 2023. Cosmic rays, processing water ice over hundreds of millions of years of interstellar transit, produce molecular hydrogen trapped in the ice. Solar heating releases it. That gives you the acceleration, with no visible coma, no exotic composition, and nothing unusual about the object at all. The headline at the time was that Oumuamua was a comet after all. David Jewett, one of the astronomers who discovered the Kuiper Belt, gave the assessment that has held up. The object is physically unremarkable, except for its highly elongated shape. The second visitor is a better story about people. 2I, Borisov, was discovered on the 30th of August, 2019, by Gennady Borisov, an engineer at the Crimean Astronomical Station, using a 65-centimeter telescope that he had built himself. Every professional survey in the world was running, and an amateur instrument made by hand found it first. It was unambiguously a comet. It had a coma and a tail from the start, and behaved, to first approximation, exactly like an ordinary comet that happened to be on an unbound orbit. But its chemistry was not ordinary. Its ratio of carbon monoxide to water measured between 130 and 155%. More frozen carbon monoxide than water. That is a far higher ratio than any comet ever measured in our own solar system. The interpretation is that it formed in a carbon-rich disk around a cool red star, in conditions considerably colder than the region where our comets formed. And then, on the 1st of July 2025, the third one was reported to the Minor Planet Center, found by the ATLAS survey telescope at Rio Hurtado in Chile. That survey is part of the Planetary Defense Network. It is funded to look for things that might hit us, and it found something that could not. 3I ATLAS was about 670 million kilometers from the Sun when it was found, inside Jupiter's orbit. It approached from the direction of Sagittarius, toward the galactic center. Its orbital eccentricity is about 6.1. For comparison, the first visitors was about 1.2. Anything above 1 is unbound, but 6 is another category entirely. Its incoming speed was 58 kilometers per second, more than twice the first object's, and at its closest to the Sun, it was moving at about 246,000 kilometers per hour. Its orbital inclination is about 175 degrees, which means it came in almost exactly backwards relative to the planets and within about 5 degrees of their plane. It reached perihelion in late October of 2025 at about 1.4 astronomical units, just outside the orbit of Mars. And here is the timing, which is the most quietly remarkable thing about the whole encounter. At the moment of its closest approach to the Sun, Earth was on the opposite side. The object's angular separation from the solar disk, as seen from here, was 12.8 degrees. Which is close enough that pointing anything at it means pointing very nearly at the Sun. So consider what that week actually looked like. There is an object arriving from another star, moving faster than anything of its kind we have recorded, on a path that will never bring it back. It is making the single closest pass it will ever make to any star, and everything volatile in it is being driven off at the maximum rate it will ever experience. And for those days, humanity cannot look at it. Not because we lack the instruments. We have a telescope at the second Lagrange point, and another in low Earth orbit, and dozens on mountaintops, and the geometry simply forbids it. The Sun is in the way. Every observatory on the planet is pointed elsewhere by necessity, waiting. It had traveled for something on the order of 7 billion years, and it arrived at the one configuration that made it unobservable for a week. It reappeared on the far side of the Sun in early December of 2025, and observations resumed as soon as it cleared the glare. Its closest approach to Earth came on the 19th of December at 1.8 astronomical units, about 270 million kilometers. It was never remotely a hazard. It passed Mars on the 3rd of October, close enough that Mars orbiters attempted observations, and passed Jupiter in March of 2026. On size, the honest answer is a wide range. Hubble constrained the nucleus in August of 2025 to not less than 440 meters and not greater than 5.6 kilometers. That range is deliberately wide, and it is the actual state of knowledge. A 20-kilometer figure circulated in early reporting and is not supported by that measurement. The real science is the composition, and it is genuinely unusual. The James Webb Space Telescope, observing on the way in, found a coma dominated by carbon dioxide, with a carbon dioxide to water ratio of 7.6. That is among the highest ever observed in any comet, and it sits 4.5 sigma above the trend line for ordinary comets at comparable distance from the Sun. Water was only about 4% of the outgassing by mass. Carbon monoxide, carbonyl sulfide, water ice and dust were all present. The interpretation is a nucleus that is intrinsically rich in carbon dioxide, either because its ices were exposed to more radiation than ours, or because it formed near the carbon dioxide ice line in whatever disk produced it. And then there is the age, which is the reason this object belongs at number 2. A model developed at Oxford and at the University of Canterbury combines data from the Gaia mission with models of protoplanetary disk chemistry and the dynamics of the galaxy, and predicts the likely properties of an interstellar object from its trajectory alone. It was published within days of the discovery, making this the first real-time test of the method on a brand new object. The result is that this object arrived on a steep path tracing back to the thick disk of the Milky Way, a population of older stars typically 10 to 12 billion years old, which puts the object itself at roughly 7 billion years. It was already drifting through the galaxy for nearly 3 billion years before the Sun existed. The characterization used was that it is very likely to be the oldest comet we have ever seen. That number is a statistical inference from motion, not a measured age. It is a probability distribution, not a date on a certificate, and it should be described that way. There were also anomalies reported, and they were widely amplified, and it is worth handling them the way the field did. Jason Wright at Penn State, who directs a research center devoted to the search for technosignatures and is therefore not a debunker by temperament, published a point-by-point response in November of 2025, having consulted 4 planetary scientists. His assessment is a good model of how this reasoning works. Several of the claimed anomalies dissolve under scrutiny. The improbability of the trajectory alignment is a post hoc calculation, where the properties whose odds were computed were chosen after they were known. The claimed nucleus mass rested on assuming the acceleration was measured about 1,000 times more precisely than it actually was. And a claimed alignment with the direction of a famous 1977 radio signal to within 9 degrees is not an alignment at all. 9 degrees is an enormous distance on the sky. But 4 of the anomalies do genuinely interest planetary scientists, and they should be named honestly. A very high nickel abundance relative to iron. An extreme negative polarization, stronger than has been seen in any comet before. The strange water abundance, and how rapidly it brightened on the way in. And all 4 are exactly the kind of anomaly you would expect from a new kind of comet. It is from a different star system, with a different composition and a different formation history. It took a different route through the galaxy and experienced different radiation. It is a different age. And, most importantly, it is falling toward the Sun so much faster than any comet from our own outer system that at any given distance it has had far less time to warm up. Unusual heating behavior is what you predict, not what surprises you. The structural point applies to every object of this kind. Comets are notoriously individual. The aphorism in the field, attributed to the observer David Levy, is that comets are like cats. They have tails, and they do precisely what they want. Every bright comet is strange in some new way. NASA's own position was stated without hedging. Its characteristics, color, speed, and direction are all consistent with what we expect from a comet. It is now past everything. Past perihelion, past Earth, past Jupiter, fading, on a path out of the solar system, never to return. It left at the same 58 kilometers per second it arrived with, and its fading light curve shows no evidence of any light it produced itself. So why does this rank at number 2, above the mathematics and above the probes? Because the transfer of rock between worlds is not a hypothesis. It is a catalogue. As of 2020, 277 meteorites had been classified as Martian out of about 72,000 classified meteorites. Less than 0.5%, but not zero, and confirmed since 1983, when gases trapped in impact glass in one of them were found to match the Martian atmosphere as measured by the Viking landers. The famous one was found in the Allen Hills of Antarctica on the 27th of December 1984, and the person who picked it up was Roberta Score. It weighed 1.93 kilograms and crystallized about 4.09 billion years ago. Carbonates formed in its cracks at about 18 degrees Celsius in water near the surface. It is the only Martian meteorite we have from a time when Mars may have had liquid water. It was ejected 16 to 17 million years ago and landed here about 13,000 years ago. On the 6th of August, 1996, a NASA-led team announced possible traces of biological activity in it, and the President of the United States made a televised statement about it the following day. The claimed signatures were tiny ovoid structures interpreted as fossil bacteria, magnetite crystals arranged in uniform domains, and organic molecules concentrated around the carbonates. Every one of them has since been reproduced or explained without life, and the current consensus, published in 2022, is that the organics formed through water-rock chemistry on early Mars. Not life. The methodological lesson from that literature is one sentence, and it applies to everything in this video. Morphology cannot be used unambiguously as a tool for primitive life detection. And yet that meteorite is considered the turning point in the history of astrobiology. The paper and the attention it drew are what built the modern field. The wrong answer created the discipline that can now ask the question properly. But the single strongest fact in the whole argument is a temperature. That Antarctic meteorite reached Earth's surface without ever being heated above about 40 degrees Celsius since it left Mars. Not during the impact that launched it. Not during 16 million years in space. Not during entry. Microbes in the interior of such a rock could have survived the entire journey with room to spare. Transfer between stars is much harder. The probabilities for the general case are very low, and they depend heavily on low-velocity exchange, which is far more efficient while a star is still inside the cluster it was born in, where separations are small and relative speeds are gentle. If it ever happened, that is when it happened. Which brings us to why the sample size is about to change. The Vera Rubin Observatory sits on Cerro Pachón in Chile, carrying the largest digital camera ever built, at 3,200 megapixels. Its first images were released on the 23rd of June, 2025. Its alert stream began in February of 2026. And its 10-year survey of the southern sky officially began at the end of June this year, about 6 weeks ago. It takes a new image roughly every 40 seconds, about 1,000 images a night, about 10 terabytes of data a night, and each point in the southern sky gets revisited about 800 times over the decade. In roughly 6 weeks of early optimization surveys, before the real survey even began, it discovered over 11,000 asteroids that nobody had ever seen. On how many interstellar objects it will find, the published estimates disagree by more than an order of magnitude, and the honest thing is to say so. One modeling range gives anywhere from 0 to about 70 per year. A more conservative estimate gives 5 to 50 across the entire 10-year survey. Somewhere between a handful and dozens over the decade, and nobody yet knows which. But the framing is what matters. We found 3 interstellar objects in 8 years, using instruments that were not looking for them. One of them was found by an amateur telescope built in a workshop. Rubin is looking. 3 objects in 8 years, found by accident, and the first instrument ever built to hunt them started work 6 weeks ago. Which means the sample size that will settle whether anything rides along is about to stop being 3. Every entry so far has been about them. The last one is about us. And it is the only entry on this list whose evidence is already complete. Number 1, the window. Every entry on this list so far has been about them. How they might sleep. How they might be stuck on a heavy world. How they might have lived here and left nothing. How we might deliver them ourselves or mistake ourselves for them. How one of them might be parked 20 kilometers from a spacecraft right now. The entry at number 1 is about us. It is the only scenario on this list whose evidence is complete, entirely public, and produced by our own instruments. And it is at the top because of that, not because it is the most alarming. The claim is this: being detectable is not a property a civilization has. It is a phase a civilization passes through. And if that phase is short, then the galaxy could be full, and the sky would look exactly like this. 3 bodies of evidence support it. All 3 are measurements. All 3 are ours. The first is that every survey ever conducted for large-scale engineering has come back empty. Start in 2009 with a physicist named Richard Carrigan at Fermilab, working from data collected by the infrared survey satellite IRAS. He was looking for the waste heat of a Dyson sphere, a structure enclosing a star to capture its output. Such a thing cannot hide, because thermodynamics does not permit it. Energy captured is energy that must eventually be re-radiated at a lower temperature in the infrared. His funnel is worth walking because the shape of it is the finding. 245,889 sources in the catalogue, down to 11,000 with usable spectra. Down through quality and temperature cuts to 6,500, then 2,200, then 1,500. 295 examined by eye. Then 65. Then 22. Then 16 described as somewhat interesting. And finally 3 described as most interesting but with questions. The reach was real. That instrument could, in principle, have found a Dyson sphere of solar luminosity out to 300 parsecs, a region containing on the order of 1 million sun-like stars. And it covered 96% of the sky, which makes it, in Carrigan's own description, one of the only whole-sky searches of this kind ever conducted. His verdict was this: with several possible exceptions, all the good sources identified in this search have some more conventional explanation. In spite of the fact that there are many mimics, such as stars in a late dusty phase of their evolution, good Dyson sphere candidates are quite rare. His rough limit was that fewer than 1 in 10,000 of the sources could possibly be one. The best candidate in the entire sample turned out to be a carbon star. Hold on to that number for a moment. 1 in 10,000. Then, in 2015, a group at Penn State ran the same idea at a scale that is difficult to hold. They did not look for enclosed stars. They looked for enclosed galaxies on the reasoning that if the step from stellar-scale engineering to galaxy-scale engineering is fast, then a universe with common spacefaring life should contain many galaxies whose starlight has been substantially reprocessed into infrared. They examined the roughly 100,000 galaxies their instrument resolves. And their result is one sentence. No galaxies in our sample host an alien civilization reprocessing more than 85% of its starlight into the mid-infrared. The reddest object they found turned out to be an active galactic nucleus in Virgo. And then the most recent, which is the one that matters most, because it is the only search that produced candidates, and it shows what happened to them. A team at Uppsala, in what is described as the first Swedish SETI project, ran 2 searches. The first, in 2022, established limits. Fewer than 1 in 50,000 stars within about 326 light-years could host a Dyson sphere that is 90% complete and operating at 300 Kelvin. Their own honesty about that result foreshadows everything that followed. Young stars wrapped in dusty cocoons and old stars ejecting dust as they die are significant interlopers in the current study, they wrote, and likely dominate our upper limits. The second search, published in 2024, is the one that made headlines. About 5 million objects within 300 parsecs, down to 320,000 with the right infrared detections, down to 11,000 that fit the models. Through a neural network classifier, then down to 368 with adequate signal to noise. And then, by visual inspection, 7. Of those 368, 89% were blends of multiple overlapping sources, and 7 were candidates. All 7 were small red dwarf stars, between about 470 and 900 light-years away. The authors were careful about what they had shown. It is definitely premature, they wrote, to presume that the mid-infrared presented in these sources originated from them, and it is essentially impossible to prove the existence of a Dyson sphere from photometry alone. Their own arithmetic predicted that about 2 of the 7 would turn out to be chance alignments. The real answer arrived faster than that. Within weeks, another group cross-matched the 7 positions against 5 radio surveys and found radio sources at 3 of them. Their conclusion was that all 7 candidates had very likely been misidentified, contaminated in the infrared by background galaxies full of hot dust. And then, in January of 2025, they went and imaged one properly. 9.5 hours on a British interferometer array, followed by a European very long baseline network including the 76-meter Lovell dish and the 100-meter Effelsberg dish. The radio source resolved into a single compact core with a brightness temperature above 100 million Kelvin and a flat spectrum. That is an active galactic nucleus, a supermassive black hole feeding in a galaxy far behind the star. And here is the detail that makes the whole thing land. The short wavelength infrared position sits on the star. The long wavelength infrared position shifts east onto the radio source. There is no radio emission at the star's own position at all. A background galaxy, about 5.5 arcseconds away on the sky and billions of light-years away in reality, was leaking into the measurement and making an entirely ordinary red dwarf look like it had been enclosed by something. 3 classes of whole sky search across 16 years at 3 scales. 1 star, 1 million stars, 100,000 galaxies, all null. And the only candidate set anyone produced dissolved under a better instrument within 8 months. The second body of evidence is about our own voice, and it goes the opposite way to what almost everyone assumes. The standard picture is that Earth broadcasts loudly, that a bubble of our television and radar has been expanding outward since the 1940s, and that anyone within about 80 light-years is currently receiving Second World War-era transmissions. That picture comes from a real study, published in 1978, which concluded that our most detectable signals were military radar systems and television stations. It was true then. It is not true now. A study published in 2023 by researchers in Mauritius and Manchester revisited it, and the framing sentence is the important one. The nature of the Earth's radio leakage has changed significantly since the pioneering work of 1978. Powerful television transmissions, they write, are no longer a major contributor to Earth's leakage radiation with the rise of cable and the internet. So they modeled what our mobile network looks like from 3 nearby stars. The peak power leaking into space from all of our mobile infrastructure comes out at about 4 gigawatts, associated with 4th-generation technology over the east coast of China, viewed from a star roughly 8 light-years away. And then the finding. That leakage could not currently be detected by a nearby civilization located within 10 light-years of the Earth, using instrumentation with a sensitivity similar to the Green Bank telescope. Run it backwards and it is worse. Any existing extraterrestrial civilization leaking radio signals from mobile towers at the same power levels would not be detected by the Green Bank telescope either. The arithmetic is simple and unforgiving. The minimum detectable equivalent power at 10 light-years with that telescope is 1.4 times 10 to the 13th watts. Our leakage is 4 times 10 to the 9th watts. We are roughly 3,600 times too quiet. And the scale of the thing generating that signal is what makes the smallness land. There are almost 11 billion mobile connections on this planet, against roughly 8 billion people. All of that running constantly, and we are still 3 orders of magnitude below the threshold at which our nearest neighbor could hear it. There is an irony sitting on top of this, and it is recent. While our broadcasting has been getting quieter, our accidental emission has been getting louder, and it is coming from orbit. Radio observations in 2022 found unintended electromagnetic radiation from 47 of 68 Starlink satellites that crossed the telescope's beam, at frequencies with no relationship to their actual downlinks, including a set of lines that may be harmonics of a 25 MHz clock signal inside the spacecraft. Follow-up observations in July of 2024 detected all 97 second-generation satellites that crossed the beam, and found them on average 15 decibels brighter than the first generation in the band protected for radio astronomy. That is a factor of 32. The regulatory position is stated in the papers without editorial. Any kind of unintended emission is not subject to spectrum management of active radio services. It is currently not well regulated for satellites and spacecraft. And the warning attached is that tens of thousands more are being built, and without proper consideration, these could produce an artificial sphere of radio light that renders some astronomical observations impossible. Those papers are about protecting astronomy. They do not mention the search for technosignatures at all. But the inference is available, and it is this: unintended, narrowband, harmonically related emission from technology is precisely the signature class the search hunts for. We now produce it in orbit, in quantity, without regulation, and it is filling the instrument we would use to hear anyone else. Which brings us to the third body of evidence. The Arecibo Observatory was a 305-meter dish built into a sinkhole in Puerto Rico, made of 38,778 perforated aluminium panels, completed in November of 1963. An 820-ton receiver platform hung 150 meters above it, from 18 main cables strung between 3 towers. Each of those cables was an 8-centimeter bundle of 160 individual wires, painted and continuously purged with dry air to keep moisture out. It was the largest single-aperture telescope on Earth for 53 years. And its radar was extraordinary. 3 transmitters, the strongest of them delivering an effective radiated power of 22 terawatts. That dish is how we mapped the surfaces of asteroids and measured the rotation of Mercury. It is also the instrument from which humanity sent its only deliberate interstellar message at scale, and it sent it once. On the 16th of November 1974, at a ceremony marking the telescope's remodeling, it transmitted 1,679 binary digits, about 210 bytes, at 450 kilowatts, at 10 bits per second. The entire broadcast lasted under 3 minutes. The number 1,679 was chosen because it is the product of exactly two primes, 73 and 23, so the digits can be arranged into a rectangle only one useful way. The other arrangement is noise. It encoded the numbers 1 to 10, the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the formulae of the DNA nucleotides, and the size of the human genome, with a graphic of the double helix. The average height of a person, encoded as 14 times the wavelength being used. The world population. A diagram of the solar system with the third planet raised, and a diagram of the telescope itself. It was designed by Frank Drake, with contributions from Carl Sagan. Two of its facts were already wrong or about to be. The genome size it encodes is about 4.3 billion base pairs. The real figure is closer to 3.2. And the population was 1974's. It was aimed at Messier 13, a globular cluster about 25,000 light-years away, chosen because it was large and conveniently overhead at the time of the ceremony. It will not be in that position when the message arrives. And it was never really meant as a conversation. In the words of the people who built it, it was meant more as a demonstration of human technological achievement than a serious attempt to enter into a conversation. Under 3 minutes. Once. In 50 years of trying. Then, in 2020, the machine came apart. In August of 2020, an auxiliary cable pulled out of its socket on one of the towers and cut a 30-meter gash in the dish below. The cause was incomplete molten zinc fill in the socket, which had let moisture into the wire bundle over decades. Then, in early November, a main support cable from that same tower snapped. On the 19th, the decision was made to decommission. By then, engineers were watching individual backstay wires break at a rate of 1 or 2 per day, and the rate was rising over the final weekend. Picture the morning of the 1st of December, 2020. It is just before 8, local time. There is nobody on the platform and nobody underneath it, because the site has been closed for days. The remaining cables are holding 820 tons of receiver equipment, 150 meters above a dish the size of several football fields, and they are failing wire by wire in a way that can be watched. The second main cable on the 4th tower lets go. The remaining 2 fail moments later, within seconds, because the load has nowhere else to go. And the platform falls, and as it falls it drags the cables with it, and the cables shear the tops off all 3 towers on the way down. Then it is quiet, and there is a great deal of aluminium in the bottom of a sinkhole in Puerto Rico, and nobody is hurt, and the largest thing humanity had ever built for the purpose of listening to the sky is finished. All 3 petabytes of data going back to the 1960s were recovered. A replacement had been designed. 1,009-meter dishes on a tiltable plate, with 500 times the field of view, twice the sensitivity, and 4 times the radar power, for $450 million. In October of 2022, it was decided that the site would not host a new telescope. There is an education center there now. Frank Drake had been Arecibo's observatory director from 1966 to 1968. What was actually lost is specific. The United States now has one high-power planetary radar. It is Goldstone, running roughly half a megawatt at around 8.5 gigahertz on a 70-meter dish, against 305. And that antenna is primarily a deep space communications asset, so radar runs on it only a small fraction of the time. There is a line from the engineers designing a possible replacement transmitter at Green Bank that conveys the gap better than any comparison of dish diameters. Describing their own pilot experiments, they wrote, "For reference, there is more power in a conventional microwave oven than was transmitted by the Green Bank telescope during these experiments." Their pilot ran at 700 watts. The design goal is 500 kilowatts. Construction funding has not been secured. The genuine replacement is being built in Australia and South Africa. 131,000 antennas at the low-frequency site, 197 dishes at the mid-frequency site. Its promise is real. It will expand the volume of the galaxy that can be searched for these signals by a factor of 1,000. At the end of last year, there were 7 dishes standing and about 15,000 antennas assembled. Full science operations are scheduled for 2032. Hold 2032 against 1974 and you have the shape of our own detectable century. Which leaves the number that decides everything, and we have never had a single measurement of it. The Drake equation was written as a meeting agenda. Drake's own account is disarming. As I planned the meeting, he said, I realized a few days ahead of time we needed an agenda. And so I wrote down all the things you needed to know to predict how hard it's going to be to detect extraterrestrial life. And looking at them, it became pretty evident that if you multiplied all these together, you got a number. The meeting was at Green Bank in 1961. 10 people attended, including Drake, the chemist Melvin Calvin, the engineer Barney Oliver, and a young Carl Sagan. They called themselves the Order of the Dolphin and put a plaque on the wall. They were reasonably confident about most of the terms. On the final one, the average lifetime of a communicating civilization, they wrote down a range from 1,000 years to 100 million. And here is the result the whole video has been walking toward. Given the uncertainties, the meeting concluded that the number of communicating civilizations in the galaxy is approximately equal to that lifetime. Every other term multiplied together came out near 1. The entire answer collapses onto the single quantity for which we have never had one data point. Drake's own suggestion was that a large number of civilizations form, and that the lack of evidence may simply be because they tend to disappear rather quickly. Sagan took it further, and it shaped the rest of his life. He argued that all the terms except that one are relatively high, and that the determining factor is the ability of technological civilizations to avoid self-destruction. That reasoning is why he spent his later years on nuclear weapons and on the environment. And a study from 2020 made the assumption explicit in the cleanest possible way. In its strictest scenario, it found there should be at least 36 communicating civilizations in this galaxy, based on the assumption that the average lifetime is 100 years, because that is how long we have had radio. Its conclusion is the one to end on. The nearest such civilization would most likely orbit a small red star, would far surpass our ability to detect it for the foreseeable future, and would therefore make interstellar communication impossible. At number 8, a few centimeters of ocean sediment held the entire industrial history of this planet. That was a fact about geology. At number 3, the same thinness appeared as a window in time, the sliver in which an expanding civilization is visible before it arrives. That was a fact about physics. Here it is a third time, and this version is the one we control. The interval in which humanity has been loud is a sliver of exactly that kind, and we are already thinning it ourselves, tower by tower, cable by cable, as we get more efficient at talking to each other and quieter to everyone else. And at number 7, we said the instrument decides the answer, when the petri dish and the ribosomal primer could only find the biochemistry they were designed around. At number 5, it returned as error, in a microwave oven and an intermodulation product. Here it returns as loss. A background galaxy decided that a red dwarf was enclosed, and a corroded socket decided how loud we could be. Here is the number to leave you with, and it is small enough to be almost gentle. Existing Earth radio telescopes could only detect Earth's own radio transmissions from roughly 1 light-year away, not the nearest star. The nearest star is 4.2. So the most plausible version of the silence is not that nobody is out there. It is that being findable is a phase rather than a state, that ours may already have peaked, and that a galaxy full of civilizations, each briefly loud, at random intervals across 13 billion years, would produce a sky that looks precisely like the one above us tonight. 10 scenarios, ordered by evidence, and the one with the most evidence behind it, turned out to be about how briefly anything is loud, including us. There is no answer at the end of this list, and there was never going to be one. There is only a better sense of the size of the question, and of how narrow a window we are looking through, and how quietly the universe declines to fill it. Let that stay with you for a while. Sleep well, and good night.